Testing. How does this sound? Testing, testing. Uh, can you guys hear me okay? Sounds good? Okay. All right, cool.
I heard the warning relaxation and finance. Oh my gosh.
Oh, yes. Yes. So you eventually logged out of Steven's.
Test.
Okay, sounds good.
Okay, hello everyone. So I am Xavier Rival. I am going to chair this first session on program analysis. So welcome to the Dortoir room, which is where I guess people used to sleep. So, but we are not going to sleep today. We are going to start with program analysis talks. So, and first, the first talk will be given by Gregory Blake on a modular static cost analysis for GPU warp level parallelism. So please.
Good morning. Thank you for coming to a modular static cost analysis for GPU warp level parallelism. My name is Gregory Blake. This is work done with Hannah Zurcarelli, Udaya Satyamurthy, Julian Lange, and Tiago Cogombrero, work done at UMass Boston in collaboration with the Royal Holloway University of London. Today we're going to be talking about why GPUs matter and the challenges of analyzing performance bottlenecks. We'll go over what it takes to analyze GPU kernel performance, give some theory, the relational cost analysis of GPU kernel analysis, and then go into our implementation, Pico, which is a tool to analyze GPU kernels. So why do GPUs matter? And what are the challenges in analyzing those performance bottlenecks? Performance is the raison d'etre of GPU programming. Consequently, GPUs are everywhere. The LLM revolution is powered by GPUs, where GPT-5 was trained using 200,000 GPUs. Scientific advancement is powered by GPUs, where 9 out of 10 of the top supercomputers are powered by GPUs. And so we want to be very careful with GPU programming, since it's such a desirable property for performance. Developers for GPU programs really want to manage those resources well. They want to maximize parallelism, where more work done concurrently means less time consumed, optimize memory access, because there's only so much memory bandwidth to go around, and to do that, they need to understand the computational model of GPUs, which is single instruction, multiple thread, and manage the control flow for those threads. And because we're so interested in their performance, that these programs are intended to run fast, we want to understand how they work. And there are several approaches for doing this. NVIDIA has a profiler, Nsight, which is a dynamic analysis. It provides no worst case analysis, just counts the number of problems that occur, and provides some symbolic execution tools as well, which detect only the presence, but not the frequency or cost of some of these bottlenecks. And there are also static approaches. Pug and GPU Drano detect the location of these performance bottlenecks, but not how frequent. And the state-of-the-art Rakuda has limited support for GPU-specific semantics, which lead to over-approximations, and cannot reason about the precision of the analysis. That is, there's no exact costs. So the problem of cost analysis for GPU kernels is very important to us. We want to understand the cost of that performance bottleneck. And in doing so, we want to account for how many resources are needed to run the program. And we want to motivate counting active threads per memory access as one of those approaches. In this summary slide, we have a CUDA program, and we're very interested in how many read accesses happen here highlighted. And over the next few slides, we're going to talk about how we get to this solution where the cost is W squared plus W over 2, where W is the number of concurrent threads. So why is that cost W squared plus W over 2? And to do that, we need to understand warp semantics. So for that CUDA kernel that we have one particular interesting variable at the top, that thread idx.x, which is a unique thread identifier provided to every thread in a warp, which is a collection of threads that are executing in kernel lockstep. That is, every instruction in the thread happens at the same time. And then some of those threads may be enabled or disabled, depending on the control flow of the program. So in an example where we have 4 concurrent threads, we have this view of that same for loop, where each of that thread idx.x, which I might call the thread ID, is replaced with its unique identifier, and we have those 4 loops. Now let's kind of understand how it executes. In the beginning, we have all of our threads running. There are 4 threads that access this array for reading. We increment x as usual for a for loop, and one of our threads terminates because its test condition no longer passes. And likewise, and then as we move along, only 3 threads are active. Increment again, another thread disables, and this continues with each thread disabling as it progresses until no threads are active and the loop terminates. So counting that active threads per memory access gives us this nice triangular shape, which allows us to give a series summation for the number of active threads and the number of read accesses in the loop. And so thread divergence, which is this property of each of the threads being enabled or disabled separately from the rest, is an important core aspect of 2 major performance bottlenecks, bank conflicts and uncoalesced accesses, both of which are memory performance issues where threads are competing for memory bandwidth. And the key takeaway for all of this is that precisely characterizing that thread divergence is precisely characterizing the performance bottlenecks. That takes us to our cost analysis, which is our contribution. We translate the concurrent warp semantics into a sequential program and then build on the vast literature of cost analysis of sequential programs. We do that in these steps. The CUDA kernel, there on the left in A, is translated into our intermediate representation, memory access protocol, where we remove a lot of the details of the execution of the program and focus just on the memory access. We then translate that concurrent program into a sequential cost program with our analysis, and then use regular sequential cost solvers to reduce this into an expression. And the major contribution here is to prove the correctness of step 2, that translation between our intermediate representation and a sequential cost program. And that looks a little like this. The sequential program captures the control flow of the warp and offers us this tick expression, which shows how many resources are consumed each time this part of the program is executed. And off-the-shelf tools can help reduce this into our symbolic expression. And so if we replace this with our four threads in our warp, as we did before, we can see that we have the number of active threads is the same as the cost from this enumeration. And so as we progress, one thread terminates and our cost reduces. And again, this sequential program was produced by our analysis. And as we progress, we continue to see that these maintain the same value until the thread terminates, or the loop terminates. So how can we guarantee that sequential program captures the cost of warp semantics? And that's the theoretical framework that we built to relate the cost of the concurrent and the sequential programs. And that is to show that the two programs have the same cost. Here, for our expression, we have gamma as our usual typing environment. Phi is a vector of Boolean expressions, which represents the active threads. P is our concurrent warp protocol. Tilde our parametric cost relation, and S is the sequential cost program. And that cost relation, equality greater than, less than, allows us to bound the relationship between the two costs. So let's go through an example. Here we have our closed environment, and we start with all of our threads being true or active. We have that protocol here on the left. In this case, this is partially through our analysis, so that access to array A is not a typical like C++ array access. It's a vector of costs that come after our analysis. We have the sequential cost here on the right with the analysis of the tick with W minus X being the cost and equality between them. So what does it take to prove that those loops have the same cost? We need to prove that the iteration spaces have the same number of iterations. And in this case, we also, we see that it is of type D divergent, that the threads are not all the same at the same time, which would be a uniform thread. We also need to prove that the bodies have the same cost. In this case, we have a subscript for that divergence for the ranges where X holds this divergent property, and the cost relation between them. And we can see here on the right what we saw earlier from the example of the costs between the scalar and vector costs. And here's where that array access is a series of numbers. So that thread divergence is captured in the type annotation for X. We see that we have exact costs and the symbolic costs per iteration. And our theory is driven by two core ideas: that loop analysis, which allows us to relate the iteration spaces, and a metric analysis, which allows us to relate the symbolic cost, which is a parameter of our theory and why this is a modular static cost analysis. More generally, the capital I is the loop analysis to do that relationship for the two ranges, so that if they are the exact same ranges, we can use the same, or if they are bounded above or below, we can use those instead. We compare the loop body while recording the original ranges of X, and we track the uniformity and divergence of the threads in the type system. And so our main result here, so given a metric and a cost relation, if we can derive the cost statically for a protocol P and a program S, then that cost holds dynamically. And the key contributions from this are that the warp semantics are we support warp semantics with thread divergence, which was not previously supported. We can also add the lower and exact bounds, which before we were only able to handle upper bounds, and it's all handled in the same formalism. And we also offer symbolic costs per iteration, where there were only fixed costs before. And all of this has been proven sound with mechanical proofs in Rock. And so we didn't want to just build out to this theory. We also wanted to test this, since this is used for performance and practical needs. And so we built out a tool, Pico, which follows a very similar pipeline to what we described earlier, where we analyze a CUDA program, extract it into our protocol, our intermediary representation, and perform some analysis, which optimizes our intermediary representation, does the loop and metric analysis, both for uncoalesced accesses and bank conflicts, which proves out that that we are able to use this type theory. And then we support a variety of sequential cost analyzers to do the final analysis, using mostly Maxima as a computer algebraic system. So how does Pico compare to the state-of-the-art raw CUDA? We would like to know how it compares, and so we reproduce the same evaluation that was used by raw CUDA in their POPL'26 paper. And then how often does control flow affect the accuracy of Pico? And so we used a large suite of well-known kernels to evaluate our tool. So in comparing with the state-of-the-art, we are able to add the thread divergent loops, the arbitrary loop steps, bitwise operators, C++ features. And in the 25 programs that were part of that initial evaluation, Pico was able to give tighter bounds in all cases, or 15 prior with CUDA. 10 of those kernels had problems of some type, and we were able to address those. And in 4 cases, we were able to document unsound bounds in raw CUDA where we did not have the same. And how frequently does this affect the control flow? In that large data set that we had mentioned, we wanted to just show that this is practical, since it is going to be helping developers in the end. So of those 226 kernels, the vast majority of the conditionals and loops, at 75% of conditionals and 85% of loops, could be precisely characterized. So we were able to say precisely the bounds that each of those loops would have at runtime, which is, I'd say, pretty good. And I am talking very fast, so in conclusion, we developed a relational cost analysis for warp-level parallelism, and with that support for thread divergence, which is that major contribution. We have correctness for exact over and under approximations. We mechanized all these proofs results in Rock, and Pico achieves the lowest bound in all of those evaluated kernels, 1.7 times better on average. In the future, we want to trade off performance, analyze performance and precision in our metrics. That, of course, we can analyze further to try to bump up that level, but that will come as a trade-off for computation. And we want to be able to report this feedback usefully to developers so that they can inspect their own programs and understand how to make changes. And now that we have a formalism, we can use this for potential program repair to say that if there is a better arrangement of some part of the program, we can report that to the user and offer it to them. So thank you for your attention, and do you have any questions?
Okay, thanks a lot, Gregory. So we have time for questions. So I see there is one over there. So we'll start.
Hi, thanks for the talk. You focused on the correctness of the step 2 in your pipeline, and I wonder about step 1. Mm-hmm. How sure are you it is correct?
That the relationship between CUDA and the intermediary representation?
Right.
That was done earlier in our lab. We have another paper on that, on the parsing of the program into the intermediary representation. And I believe we've also formalized that as well.
Okay, thank you. So maybe I will just inject a question that is very related to this one. In this first phase for transition, do you also have the possibility of losing precision, that is, of getting a program after translation that would not let you infer as precise a property as the initial one, or is it exact with respect to the properties that you try to infer later?
I'm sorry, could you repeat the second half?
So when you mix program transformation and static analysis, sometimes you have to be careful whether the transformation done before the analysis may make the job of the analysis harder, because maybe the properties of the translated program are less strong as the initial one. Is it okay? Yeah.
So the intermediary representation focuses just on the memory. Let's see, where do I have this one? Just on the memory access. So the control flow, the intermediary representation basically just manages all of the control flow. And so the analysis that goes into proving that that is the correct control flow this was we get rid of all the information that's not necessary for it. And as we progress from the concurrent to the sequential cost program, I'm just not putting the words. Julie, would you be able to say that thing?
So if I can, I will go on this step.
Yeah.
So the first step, the translation, in fairness to Greg, is a previous paper we studied in detail. So what we lose when we go to memory access protocols. And there are some conditions, some programs where we will lose some correctness, but this is quite well identified, and we can actually precisely explain where we lose this. So this was not the focus on this paper, so this is not, this is why we don't show this that much here.
Mm. Thank you. So.
Thank you very much for the lovely talk. So you mentioned in your future work that you're considering giving some bounds on average costs. This would be averaging over what?
This is mostly for reporting, so we're not really sure how to present it to the end user. We have exact costs right now, and we would like to be able to present it so that it's very useful. We're not sure what the users would appreciate the most.
Because right now the problem is that the exact costs might be data dependent and so hard to read, or?
It could be a bit complicated to read, or where to break it down, what to recommend at which stage of the process.
Thank you.
Okay.
Perhaps a tangential question. Could Pika be used, for example, as an oracle to run optimizer, optimize the code?
That's somewhat what we're thinking for the relational cost for the repair part is as an oracle, yes.
Okay, so before I move to the next question, maybe the next speaker can start to move on to start to get ready. Thanks.
Thanks for the nice talk. It wasn't clear to me what fragment of CUDA you're handling. Is it, what kind of synchronization primitives are you supporting? Are you supporting tensor cores?
So a lot of the features are a little bit dated in CUDA but most of the for a lot of the for the CUDA kernels that are available out there, we pulled down a lot of open source programs to verify that what we are able to analyze is actually what's used in practice. We do handle quite a bit of them, but we do not account for all of the newest features from CUDA.
So you do support barrier synchronization and warp level synchronization and so on?
Well, synchronization for these metrics wasn't necessary because we're only interested in reading and writing, but not necessarily that it is managed without like data races.
Okay.
Thank you. I was curious to what extent you think this pipeline could be applied to, say, web GPU kernels or other kinds of GPU architectures, how specific it is?
At the moment, this handles just NVIDIA CUDA. We are investigating what you just said in the browser and like
yes.
web GPU.
Right. Yeah.
But we haven't finished that research yet.
Okay, thank you.
Mm-hmm.
Okay, any more questions?
Thank you for the talk. You mentioned at some point that you found unsoundnesses in Rakuda. I didn't get from what you said. You said like we did not find as good bounds or something. Can you elaborate a little bit on how did you verify that those were like unsoundnesses in Rakuda and not imprecisions in your tool or something like that?
One, we went and looked at them and analyzed them by hand, and then we went by, and using our formalism, we went through those kernels in Rock and proved them out.
Okay, thank you. Any more questions? Okay. So maybe we can take a last question before while the speaker is setting up the next speaker. So is there any other question?
I was wondering, often the way you write a program and small details may make it analyzable or more precisely analyzable, if you see what I mean. Did you notice like small changes in these kernels that you analyze, in which one case you get a precise result and in another case you get a worse result? And can you maybe explain the kind of things that people need to avoid if they want a precise result?
Well, thread divergence is the source of approximation. Otherwise, this would be, if all the threads were uniform, they would be sequential, essentially. And so if they're hoping to minimize approximation, they have to find a way of keeping it uniform, and that's, of course, the challenge. And that's why we have our tool.
Okay, thanks a lot again, Gregory, for the presentation.
Right.
Okay, so we are now going to move to the second presentation of this session, which is CHISA, Static Analysis for Lightweight CHISA Verification, and the talk will be given by Chikai Tree. So please go ahead.
Okay. Hello, everyone. My name is Jiacai Cui. I'm a second-year PhD student from Nanjing University, advised by Yue Li, who co-runs the Pascal research group with Tiantan. Today, I will present our work on CHISA, static analysis for lightweight chisel verification. I think the most unfamiliar word in this title for you guys may be chisel. So I'll start by briefly introducing chisel and then move on to our own work. Chisel stands for Constructing Hardware in a Scala Embedded Language. It is a hardware description language proposed by UC Berkeley in 2012. A hardware description language is the language that hardware engineers use to design hardware, just like how we software engineers use program languages to write our software. One of the main motivations behind the chisel is to enable agile chip development, which requires hardware development to be more efficient and more like modern software development. This vision was highlighted by John Hennessy and okay. This vision was highlighted. What happened? This vision was highlighted by John Hennessy and David Patterson in their 2017 Turing Award lecture. Chisel meets this demand by leveraging modern programming language features in Scala to enable more productive chip design. This approach has seen successful practice in both academia and industry. Despite these successes, we argue that productive design alone is not enough for agile chip development. Among all the time and effort devoted to chip development, design is not the whole picture. In fact, around 70% of the time and effort is spent on verification. According to the latest industrial study, hardware projects often employ more verification engineers than design engineers, and even require designers to devote nearly half of their time to verification tasks. This reflects the current situation that existing hardware verification methods are too heavyweight to be agile. So in addition to the productive design methodology provided by Chisel, we think there should also be more lightweight approaches for its verification. This motivates our work on static analysis for lightweight Chisel verification. At this point, a natural question is, why static analysis? To answer this, I will first briefly overview existing work on Chisel verification. All of these approaches are heavyweight, either in time or in manual effort. To be more specific, first, simulation is the most widely used approach for Chisel verification, but chip simulation is fundamentally slow. For example, it can take hours or even days to simulate just seconds of chip behavior. Second, bounded model checking suffers from the well-known state explosion problem, which makes it prohibitively time-consuming for large Chisel programs. Third, theorem proving techniques require labor-intensive construction of formal proofs. For a real-world design with millions of lines of code, it is hard to imagine how many lines of proof would be required. Finally, secure type systems introduce a prohibitive annotation burden as the code base grows. Moreover, most existing code bases, to the best of my knowledge, almost all existing Chisel code bases rely on the standard Chisel type system, and retrofitting them with a new type system would require substantial manual effort. In contrast, from the perspective of time, static analysis is more efficient, and from the perspective of manual effort, static analysis is more automated. For these reasons, we believe that static analysis is well suited as a lightweight verification approach for Chisel, especially for real-world chips with million-line code bases. In this work, we introduced the first theoretical foundation for Chisel static analysis, provide a proof of concept implementation, and show its application in lightweight Chisel verification. Our theoretical foundation starts by characterizing the essence of Chisel using a core calculus called lambda C. In lambda C, we use the syntax to capture the circuit structure and the semantics to capture the circuit behavior. And we then prove key properties of lambda C, showing that it faithfully reflects important physical characteristics of hardware circuits, which can serve as a form of retrospective validation of our calculus design. Based on lambda C, we formally define a class of hardware value flow analyses. These analyses are inspired by software data flow analysis, but are specially customized to handle hardware-specific semantics. We also prove properties about their soundness, efficiency, and precision. Building on this theoretical foundation, we developed Chisel, the first Chisel static analyzer. Chisel provides a general framework for hardware flow analysis and includes several building instances. It also offers reusable infrastructure for developing new Chisel analyses beyond existing ones in Chisel. Finally, we evaluate Chisel on representative Chisel verification tasks, including bug detection and security analysis. Our results show that Chisel offers an effective and significantly more lightweight approach, outperforming existing state-of-the-arts on large, complex, real-world Chisel designs. There are a lot of stuff in this slide, but don't worry, I know it is infeasible to cover all the details in a short talk, so I'll be brief. For the theoretical foundation, I will avoid heavy formalism and instead focus on some hardware-specific intuition that I hope you can take away. After that, I will briefly overview our implementation and summarize our evaluation. Now let's move on to the foundation. Start with a fundamental question. What is special about hardware programs? I'll give some examples. Unlike software programs containing variables, hardware programs usually contain registers driven by clock signals and exhibit explicit timing behavior. Multiple registers can be synchronized by the same clock, which means they update their values synchronously on the same valid clock age. Registers driven by different clocks can also communicate, but these typically require special clock domain crossing handling. Initialization is also more subtle than in software. A hardware register can be reset synchronously or asynchronously, and then these two choices have different semantic implications. Memory is another important difference. In software, memory is mostly an abstract model. We store values into it and we load values from it. But in hardware, memory is much more concrete. It has explicit structure and a rich timing behavior. For example, we may have synchronous read memories or asynchronous read memories, which behave quite differently, and so on. There are many other examples. From the perspective of the Chisel language, all of these appear as specific language constructs. So back to the original question, what is special about hardware programs? In short, they are full of hardware-specific language constructs that are uncommon in software and come with distinct semantics. To study static analysis for hardware programs, we need to figure out how to statically over-approximate hardware behavior. And before that, we first need to characterize the dynamic behavior of hardware programs. To address these questions, we present a theoretical foundation. To characterize dynamic behavior, we introduce lambda-C, the first calculus to capture the essence of Chisel, and prove meta-theorems about lambda-C that faithfully reflects the physical reality. You can think of these theorems as a form of retrospective validation of our calculus design because there's no way to prove the correctness of some definitions. We can retrospectively validate the definitions through the theorems derived from them. Based on lambda-C, we define and formalize the hardware value flow analysis that takes care of hardware-specific semantics I have talked about and prove essential properties about its soundness, precision, and efficiency. Our theoretical foundation is presented in about 20 pages of formal discussion. For the sake of time, I will not go into these details today, but to help build more intuition, I'd like to share one more picture from our implementation. This figure shows a hardware value flow graph for an asynchronous FIFO automatically constructed by our static analyzer. This graph is where we actually perform the hardware value flow analysis. The graph is too large to read node by node or edge by edge, but that's completely fine. You don't need to. The key idea is intuitive. The nodes in this graph represent different hardware program elements, and the edges represent different relations between them. Once we have this graph, the hardware value flow analysis reduces to a graph algorithm that abstracts and over-approximates the hardware-specific semantics encoded in the graph. So far, I have introduced some hardware-specific intuition. Next, I will briefly overview our implementation. This figure shows the architecture and end-to-end workflow of our Chisel, the first Chisel static analyzer. Given an input Chisel design, Chisel first compiles it into a hardware abstraction for analysis, and then dispatches the abstraction to the requested analysis, where a rich set of general-purpose fundamental analysis support important Chisel verification tasks. An analysis manager handles the coordination and logistics inside Chisel. Finally, Chisel produces analysis results such as bug reports or security warnings. I won't go into the implementation details, but I would like to highlight the reusable infrastructure in Chisel, which we believe is especially helpful for future research, as no prior work has developed such analysis infrastructure for Chisel. First, chair, our Chisel analysis intermediate representation. Chair is structurally simple for static analysis, while remaining semantically expressive for Chisel. Second, fundamental analysis. In addition to hardware value flow analysis, we provide a rich set of graph representations. Okay. We provide a rich set of We provide a rich set of graph representations for Chisel programs, which can be reused to develop new Chisel analyses beyond the existing ones provided by Chisel. Third, the analysis manager. It simplifies engineering tasks such as orchestrating existing analyses and integrating new ones, enabling the future developers to focus on their own analysis logic without worrying about any other logistical stuff. The only part I haven't touched on yet in this figure is chisel verification tasks, which brings us to the evaluation summary. In one word, our evaluation shows that chisel offers an effective and significantly more lightweight approach for representative chisel verification tasks, especially on large and complex real-world designs. Here, effective means that chisel can produce helpful results. Lightweight is measured in terms of analysis time and manual effort. For chisel verification tasks, we study two representative cases. The first is identifying viable assertions as a representative task for hardware bug detection. The second is detecting unintended information flows as a representative case for hardware security analysis. For large and complex real-world designs, we introduce Chisel Bench, a chisel static analysis benchmark. It contains hundreds of designs totaling millions of lines of code, including the official Trojan tests, which exercise comprehensive language constructs, sys-on-chips, a deep neural network accelerator, networks on chip, a vector coprocessor, and some security benchmarks. The benchmark is diverse, real-world, and accessible out of the box. All projects are pre-elaborated, which makes the benchmark easy to reuse by the community and saves future researchers from the tedious process of building each project from scratch. With the benchmark in place, we can now move on to the evaluation results. For hardware bug detection, Chisel provides a static assertion analysis. The key idea is intuitive. We approximate the assertion violation conditions using interval analysis and a constant analysis. We compare this approach with the state-of-the-art Chisel bounded model checker, Chisel test BMC, and obtain promising results. This table may look overwhelming at first glance, but don't worry, I will summarize the key takeaways. First, Chisel is effective on real-world projects. 8 of the viable assertions reported by Chisel were recognized by developers and scheduled for future fixes. Second, Chisel is lightweight. It completes analysis on nearly 10 million lines of code in under 4 minutes. In contrast, Chisel test BMC is inapplicable on large and complex real-world designs. While we initially expected timeouts due to the state explosion problem, in practice, the tool crashes due to various errors, which we describe in detail in our paper. For the sake of time, I will not go into these errors here. To obtain time comparisons, we additionally evaluate both tools on hundreds of small-scale designs where bounded model checking does scale. At this scale, Chisel completes analysis in about 3 seconds, whereas Chisel test BMC takes nearly 3,000 seconds, further showcasing the lightweight nature of static analysis. For hardware security analysis, Chisel provides a taint analysis, which is directly a hardware value flow analysis. We compare this approach with a state-of-the-art Chisel secure type system and obtain promising results. First, Chisel is effective. It identifies all vulnerabilities in both Chisel Flow's own benchmark and the well-known TrustHub benchmark with only 1 false positive. Second, Chisel is lightweight. It completes analysis on over 1 million lines of code using only tens of annotations and less than 1 second of analysis time. In contrast, Chisel Flow is not applicable to the million-line TrustHub benchmark. This is because it is manually prohibitive to retrofit such a large code base with a new type system, whose annotation burden grows with the size of the code base. On Chisel Flow's own benchmark, with only hundreds of lines of code, it already required more than 200 annotations to make the type system check. Whereas Chisel requires only 44 annotations, which is significantly more lightweight. In summary, our evaluation shows that Chisel offers an effective and significantly more lightweight approach for representative Chisel verification tasks, especially on large and complex real-world designs. So far, we have, well, I also speak so fast. So far, we have walked through the 3 main footprints of this work, and we are now near the end of the talk. Before concluding, I have one final thought to share. This work is also a small step in a much bigger picture, applying programming language techniques to hardware programming languages. Hardware description languages. We believe that the software's long history of managing complexity is both valuable and inspiring for the hardware community, especially as chip designs continue to grow larger and more complex. We believe there are many research opportunities in this space. In fact, we have already seen a growing body of such work at recent top-tier program language conferences. Our work is just the first static analysis attempt among them. We believe there will be many more innovations in this direction, and we hope we peer researchers can bring more values to the HDL community. Thank you very much for attention. I think I have 10 minutes left. I speak so fast because I'm nervous. This is my first academic talk and my first research work. Yeah.
Well, thanks a lot for the great talk, Jack-Hai, and well, congratulations for your first presentation. Now, when you talk faster, indeed, you get more questions, so I think we can start with questions.
Yeah, okay. So any questions?
You mentioned about the hardware-specific features that's interesting and challenging for static analysis. Do you have any hardware-specific things that makes the static analysis easier than when we consider the static analysis of full software?
Could you speak a bit slowly? I'm not good at English.
You mentioned that there's hardware-specific features that was interesting and challenging for static analysis. In defining semantics, etc. I'm wondering if you find any features, hardware features, that makes static analysis design easier
than in software.
Yes.
One easier point is that hardware is a static structure. They cannot have infinite amount of memories. When we analyze software programs, we usually assume we have infinitely much memories. For example, we can allocate tons of objects, but in hardware, everything is, the structure is statical. We cannot have infinitely many registers. We have finite numbers of those elements, which is something something easier than software. Yeah, it doesn't have a dynamic memory.
Thanks for the talk. This is really cool. You mentioned that your model over-approximates certain details of hardware. Could you explain what you mean by that?
A bit slowly, please.
You said that your model over-approximates hardware behavior, I believe is the term you used. Or is that not correct? Is that the wrong one? Something like that. It approximates, right?
Yeah, over-approximate, right.
Yeah, what does that mean?
Over-approximate means we derive a result that soundly captures all possible dynamic behavior. For example, if we say a register has a range between 5 and 8, then among all possible dynamic executions, there cannot be a value of this register not lie in this range. This is what we say, what I mean by over-approximation, as those soundness properties.
That value in dynamic execution, then? What's the over part?
Like an example of where you do that.
I may not get the questions. Do you want me to explain what does over-approximation mean, or you want me something else?
As in, why is it not perfectly accurate? Like, what makes it not perfectly accurate?
You want me to explain some loss of precision, right?
Never mind.
Oh, okay. There are many. Okay, I'll give some examples. For example, we have multiplexers in hardware programs, which is something like the if statements in software analysis, where the control flow merges. In hardware, the value flow can also merge. This can cause the loss of precision. This is one case. And the second case is about module instantiation. Hardware program has many modules that can be reused. When we reuse multiple modules, we instantiate it multiple times. And in our analysis, we didn't distinguish them. So the value can also merge at the input port of these modules. But this doesn't cause doesn't cause much precision loss because there's something different in the program than software. Typically, a hardware module does not have many instantiations as we see in the code base. they usually instantiate several times, not like a software. A function can be called many, many times. This is what we observe in real-world programs. Yeah. And this is why we didn't choose to introduce some technology like context sensitivity or something like that. Yeah.
So indeed, what you described looks like a context-insensitive static analysis by abstract interpretation. And sometimes with software, when you present developers from the results of such an analysis, they complain that they're not sure if the warning is about something real or is it a false alarm. And sometimes they ask, could you provide an actual example, an execution trace that violates the specification? Have you tried building such kind of example traces guided by the result of your analysis? Or is this future work, maybe?
In our current implementation, we just report the result. And your question is good. This is the fundamental limitation of static analysis, that it will introduce some false positives. But in our evaluation, the false positive is manageable. We have take some aggressive handling to make the results manageable for manual verification. Yeah.
Okay, so we have time for some more questions. Yeah.
Do your implementation is be Sunday, or any?
Yeah, you're right.
Any difficulties to be the Sunday? Do any difficulties you have to meet to the analysis to be Sunday, such as the reflections in Java?
Okay,
so
okay, I see your question. Our core calculus is proven to be sound theoretically, but our implementation may meet some things that cannot be sound. The first one is about incomplete programs. In hardware community, they use something called intellectual property calls, IP calls, whose implementation or whose source code is unavailable. I cannot access those source codes, so I have to make some assumptions. Maybe the value flow just be cut off when encountering those external modules whose definition is unavailable. This is a source of unsoundness in implementation. Yeah.
Okay, so maybe if the next speaker can start to come forward while we maybe take one or two more questions. So I actually have one. So you presented a static analysis for Chisel, but most of what you have presented is kind of general for hardware description language properties. So how much could you use for other hardware description languages right away, like VHDL or whatever?
Could you rephrase the question to be shorter?
Sorry?
Could you rephrase the question to be shorter? I may not get the whole.
Oh, sorry. So my question is, how much of your analysis infrastructure, like be it theoretical or implementation, could you reuse if you wanted to analyze other description languages than Chisel?
I mean, which portion of our implementation is reusable by future research? Okay, this is, I have a picture here in this slide. I think the front end, the IR, the fundamental analysis, the general purpose fundamental analysis, the graph representations, and the analysis manager they are all reusable by future research. Yeah.
I guess my question was, could you use the same IR, let's say, if you want to start from VHDL, or is it too specific and you could not?
You may. There's something different between Chisel and the Verilog or VHDL. Verilog have some high-level behavioral constructs for description hardware, but Chisel is fully synthesizable. All language constructs in Chisel is synthesizable, so our IR is about the synthesizable subset that have correspondence with physical hardware. So if you want to analyze Verilog programs, you may add some features to handle those behavioral language constructs such as OS blocks, initial blocks, or something like that. Yeah.
Okay, so thanks a lot for your presentation.
Thank you.
And for the
Thank you for attention.
Okay, there are a few free chairs in the first row, so if you are, I see many people standing. So the next presentation will be about MIRI, which is a practical undefined behavior detection for Rust, and the presentation will be given by Ralph Jung. So please.
Yes, thank you for the introduction. Thank you all for coming to this talk on MIRI and Rust. So the high-level context for this talk is that safe Rust is generally a very nice place to be in. We have a high-level type system. We have strong type safety guarantees. If you haven't used Rust, you will have to take my word for that. But you can see that Ferris, our mascot, is very happy in these green lands on the side of this nice lake. However, what Ferris doesn't know is that below the depth of that lake, there are some dangerous deep-sea monsters lurking just on the other side of the same Rust program. And so this talk is all about how we can protect Ferris from the Kraken. But before I get a bit more into detail about what this Kraken is that I'm talking about, let me give some more context on Rust. So the kind of one of the things that makes Rust unique, apart from being a low-level systems language with strong safety guarantees, is that Rust puts an emphasis on balancing safety and control. So in that sense, Rust is really two languages. On the one hand, we have safe Rust, which is the overwhelming majority of code. We don't have hard data on what that is, but 95% should be a good guess. And in safe Rust, all of these nice things that POPL'-style languages should enjoy are all true, and you get full guaranteed memory and thread safety. But sometimes, when you do low-level programming close to the metal, you have to do things which are too clever for the compiler to understand why they are correct. Sometimes you need full control over what your hardware actually can do. And then, well, what you do is no longer safe. And so this is what we call unsafe Rust. And in unsafe Rust, there is a risk of Krakens tearing apart your program. And so in this talk, we will be entirely focusing on unsafe Rust, which is not representative of most Rust programs out there, but those 5% of programs do need help to ensure that the Kraken doesn't tear their program apart. So this is what we'll be looking at for the rest of this talk. So let's look a bit into more what can actually happen in practice if you have a Kraken infestation in your program. So here we have a little example program where the first line does some complicated contortions to access some memory without actually properly initializing it, which is something Rust tries to prevent you from doing. But when you do low-level unsafe programming, we give you all the tools to shoot yourself in the foot. So this is what this program does. And then it asserts a simple tautology on the integer that it obtains that way and prints the number. And if we look at what happens when we run this program in the current Rust compiler, then well, somehow this assertion fails. So I think I need to call a mathematician because apparently we found a new integer. And it has some exciting properties. But before we call him, let's figure out what this integer is that we found by just moving this print statement one line up. And so now the program will be recompiled. And it turns out the number is 0. And also if we look at the number, the error goes away. So maybe this is more of a physics thing where we need help from our quantum friends than a mathematics thing. But clearly something very strange is going on here. Well, that is the Kraken tearing your program apart and making it very hard to reason about. And so, well, to figure out what is actually happening here, we should start reading the documentation, which of course as good programmers we did before writing this code. And in particular, this assume init function that we called here. It has some documentation saying what we have to do to use it correctly. This is an unsafe function. That's why we have an unsafe block in this code. And in the documentation, it says that calling this function without the value being fully initialized is immediate undefined behavior. And undefined behavior is code for the Kraken is unleashed on your code. And so what actually happens is that after that function call, your program is already garbage nonsense. Everything that happens afterwards is kind of an artifact of what the compiler happens to do, which is completely unstable, can change under kind of apparently harmless things that you change anywhere else in the program. It's really kind of, you're just peering into the details of the machine without any guarantees about what you get. So in other words, having this kind of undefined behavior, which happens at the end of that line of the program, makes the entire remaining execution completely unpredictable. And as we have seen, this is a debugging nightmare, right? Like you have your program do something weird, you do like some obvious println debugging, and now the behavior of the program you're trying to debug changes while you're looking at it to debug it, right? This is clearly not fun. It's not just a debugging nightmare, it's a security nightmare. Many companies have found that 70% of the critical vulnerabilities in their overwhelming C and C++ code bases are memory safety issues, and all of those are instances of undefined behavior. And so preventing undefined behavior is really a very high priority for anybody who writes code in low-level unsafe languages, and that includes unsafe Rust. So MIRI is a tool that can help you prevent undefined behavior. And even the latent UB in the version of this code where apparently everything is fine, you just get 0, is detected by MIRI. So if we go back to the demo here and we ask to execute this in MIRI, then it will tell us that there is an error in this program at the corresponding line. So we don't even get to the print line or the assertion or something. The program is already doomed before we even reach that. And there's a nice error telling us what goes wrong. So for the rest of this talk, I want to explain a little bit how MIRI actually works, what kind of bugs MIRI can detect in Rust programs, and how MIRI fares in practice when you let it loose on real-world Rust code. So to get started, how does MIRI work? Well, the crux in our example was this first line, right? That's where the undefined behavior actually happened. Everything after is just an artifact of implementation details inside the compiler. And so looking at this line again, you might be wondering, well, I mean, the documentation told us to initialize this value, but this is an I8, right? It's just 8 arbitrary bits. How can 8 arbitrary bits possibly not be initialized, right? Any bit sequence will do. We just get some number. Well, the answer is that Rust code doesn't run on real hardware. If you want to reason about your Rust code and whether it has undefined behavior or not, you can't think of it as running on something which has actual bits or the kind of hardware that we heard about in the previous talk. Instead, you have to think of the program as running on a more abstract notion of a computer, an abstract machine. And in this abstract machine, every byte in memory has 257 possible states. Actually, it's more, but I won't go into that detail now. So either that byte is initialized with one of the 256 commonly known values, or it is uninitialized, which is a distinct, separate bottom state, in a sense. So basically, every byte in memory is an option U8 or a maybe U8, or however you want to call this in your favorite language. And the way MIRI works is it is basically a direct implementation of that abstract machine. So in MIRI, memory really contains a whole bunch of option U8s. Actually, we do something more efficient for performance reasons, but conceptually, this is what happens. And MIRI will go ahead and it uses the regular Rust compiler frontend and it interprets the code using one of the IRs in the Rust compiler, interprets the code line by line, executing exactly that instruction on the Rust abstract machine, having full access to all this extra state that doesn't really exist, and therefore it can tell that a certain memory has not been initialized. And so if we zoom in a bit more about how MIRI represents memory, then the way to think about it is that we have this big address space, 2 to the 64 possible addresses, and just non-deterministically distributed throughout that space are all of the allocations which are local variables on the stack, heap allocations, global statics, and a few more esoteric kinds of allocations. And for every one of these allocations, MIRI tracks the contents of the allocation as a list of these kind of more abstract notions of bytes with an explicit tracking of which of those bytes are still not initialized. So that's the view of memory. Now, one thing that is curiously absent in this view of memory is any notion of types, which might be surprising because Rust is a strongly typed language. Surely somewhere types need to show up in whatever MIRI is doing, right? And they do show up, but it's kind of a slightly higher layer on top of memory. So the way types show up in this conceptual semantics is that we use types to describe how values are represented in memory. So conceptually, there is this grammar of values that we have in MIRI, that we have in Rust, which includes mathematical integers, tuples or lists of values, sums of values, things like that. This is like the nice high-level land that Ferris likes to be in. We have nice values. But in the end, all of those values have to somehow be in memory. And Rust is a language where you can manipulate values in their raw byte-for-byte representation. So we have to talk about that representation in the language itself. We can't just leave this as an implementation detail. And so to account for that, we have two functions that convert between the high-level form and the low-level form. And you can think a bit of this a bit like serializing and deserializing high-level values into a low-level linear format. So the encode function takes a type, takes a value of that type, and returns a list of bytes representing the value at that type. Right? And so the value of 42, for example, will give a different list of bytes depending on whether you are asking for it as an 8-bit integer or a 32-bit integer. And then, of course, we have the converse operation, which takes a type and tries to parse a list of bytes, tries to interpret it as a value of the given type. And this, of course, can fail, like all parsing or deserialization operations. And if this ever fails, we say that the program has undefined behavior. So basically, these two functions kind of convert between the high-level, nice, safe world of Ferris and the low-level Kraken land. So again, this is not actually what MIRI literally does, because it would be kind of inefficient to reconstruct these high-level values all the time, but conceptually, this is what is going on. And so if we go back to our example, in particular this assume init function, where we identified the problem to be, then what happens is, well, first of all, when we call uninit, we create a new allocation, which has just the size of 1 byte and contains this byte as uninit. And then what this assume init function does is it will try to interpret this uninit byte at type I8. And this is simply not a valid representation of any integer. This decoding fails, and therefore the program is said to have a bug. So that's how Miri works. Now let's look at some other examples of what kind of bugs Miri can find in practice. I don't have the time to go into all of the UB Miri can find, so let's look at some of the ones which are, I think, most interesting. So first of all, Miri can detect data races. It can interpret concurrent programs, which it does kind of in a similar way as to how a multi-process OS would work on a single core, right? So Miri itself is sequential, but it just interleaves thread executions. And so you can have, if you write a program like this, where you have a global mutable variable, you have your first thread mutate that global state. You have a second thread which reads from the global state. This is a classical data race, and this is undefined behavior in Rust. You're supposed to use atomic variables to do this kind of synchronization across threads. And so if you run this program in Miri, then almost always, I will get back to that later, Miri will report a corresponding bug where it points out the two conflicting accesses. So quite a bit of effort was spent on making those kind of error messages reasonably user-friendly without spending too much time and performance on tracking all the information required for that. And the way this works is that we basically took a paper that was published here at POPL 9 years ago and implemented it one-to-one into Miri. So dynamic data race detection for C++11 by Lidbury and Donaldson based on the fast-track data race detection algorithm. We kind of just took this and put it into Miri, except we had to update it because that paper described a checker for C++11, but the C++ memory model, which is shared by Rust, has changed since then, so we had to update this to C++20. So broadly speaking, this is based on tracking vector clocks throughout the program, and for all of the details, I refer you to our paper or their paper. And it turns out, by implementing that, we get more than just data race detection. Actually, we can also simulate behaviors and therefore detect bugs in programs caused by having those behaviors, which are legal in Rust, but very rare or impossible to happen on real hardware, depending on which hardware you have. So what I'm referring to here are weak memory behaviors. I brought a little example of that. Here we have a program that has two global variables. This time we are using these atomics, which we are allowed to access concurrently from multiple threads. We have a first thread which sets both of these atomics to 1, and it does this in the order of first setting x and then setting y. And we have a second thread which will first read y, and then if it reads y, it reasons that, well, because x is updated before y, if y has already been updated, surely x has been updated. So if we now look at x, we should see a 1. And if this would be a sequentially consistent program where the instructions of the two threads are just interleaved, this would be correct reasoning, and this assertion could never fail. But the ordering that is annotated for these accesses is relaxed, which means this program is allowed to have behaviors that can't be observed in a sequentially consistent execution. And indeed, some of the time, around 25% of the time when you run this program in Miri, this assertion will actually fail. And the way this works is, again, this paper that we implemented actually has support for emulating weak memory behaviors. It has explicit store buffers where we track old values for all of these atomic locations and non-deterministically give out kind of outdated values, and so we can create behaviors like that. We cannot create all legal behaviors in C++, but we can create some of them which already helped find a whole lot of bugs. So beyond these, there are a lot more kinds of undefined behavior that Miri can find, but I can't spell them all out in detail now. What I can say, the bottom line of this is that for all we know, Miri can detect all of the de facto undefined behavior in deterministic Rust programs. So let me explain these two caveats that I mentioned here in a bit more detail. So first of all, this point about de facto UB, Rust does not yet have an official specification that would say what exactly is and isn't UB, but it has a compiler that does optimizations that make assumptions about what the program does and doesn't do. So for the parts of the Rust which are still underspecified, we are working closely with the Rust compiler team and the language team and with LLVM people where necessary to figure out what are the assumptions needed to justify the optimizations that Rust does currently. And for all we know, we are checking for all of the UB that is required for that. So what this means is that if you use Miri today and you compile it on the same kind of corresponding Rust compiler version, then if Miri doesn't find UB in your program, it should be compiled correctly. But tomorrow, the Rust compiler might get new optimizations, and then maybe we have to extend a little bit our notion of UB. Right? So there's no guarantee into the future yet. That can only happen once there's a stable notion of UB in Rust. And secondly, non-determinism, I already kind of alluded to this in the concurrency part. Many Rust programs are non-deterministic, and Miri as a testing tool just explores one execution. We have a mode where we randomly explore many executions in parallel, but there is no way to exhaustively explore all executions with Miri. So if your UB depends on non-determinism, Miri might not be able to find it. The other limitations are that Miri is very slow, on the order of 4 to 5 orders of magnitude slower than real executions, which is really very slow, but also computers are fast. So you can actually still use Miri for many practical things. And finally, Miri cannot invoke functions which are not implemented in Rust. It is an interpreter for Rust programs. If your program calls some operation in another library that was implemented in C, Miri just stops. Now, to make Miri practical, we have to implement a whole lot of the kind of C operations that many Rust programs need, from simple things like printing to standard out to more complicated things like spawning threads, using pthread synchronization primitives, using futexes on Linux. There's a long list of things. And in fact, most of the work in Miri is implementing all of those operations that are outside Rust, but that Rust programs need to proceed to the remaining Rust code so we can find UB in that code. So coming to the final section of the talk, how does Miri fare in practice? Well, first of all, Miri has found numerous bugs in real-world code. This is just the table of those bugs that we discuss in a bit more detail in the paper. We have a longer list of around 30 or 40 of them on the Miri website, but this list is nowhere near exhaustive, because at this point, many of the top crates and even the Rust standard library itself use Miri in their continuous integration. So new bugs are prevented from even entering those code bases, because Miri will tell the programmer that something is wrong before the code lands. So Miri really has become a standard tool for unsafe Rust development. And you also saw this earlier. I was invoking Miri on Godbolt, right? This was the normal official Godbolt instance. Miri is part of the official nightly Rust toolchain, so I didn't have to set up my own server for this demo. This is just the official website for that. We also did a slightly more systematic evaluation by running Miri on the 100,000 most downloaded crates on Crates.io. So that's the repository of libraries for open source libraries for Rust that people share. To just briefly summarize the results, there were around 1.6 million test cases in those crates, and over 70% of those pass in Miri. So we have enough kind of C functions and things implemented, and of course all of the Rust language features to run all of that code. Around 70% of them time out, and the rest either hit an unsupported C operation or they have bugs. They actually have undefined behavior or assertion failures caused by Miri exploring things which the real code didn't hit or something like that. Now, this is, of course, only a brief summary of what, like all of the things that I could say about Miri. In the paper, you can find more details about the Miri abstract machine, various tricks we use in Miri to make it slow but not even slower, and also more details about how we updated the C++11 data race checker to C++20. In future work, we will be very interested, or we are to some extent already working on this, in also supporting invoking native libraries, but jumping from Miri directly to C code and then back to test interactions of Miri with SQLite or something like that, for example, which we won't re-implement inside Miri. So we won't be able to check bugs, to find bugs in native code, of course, but we could find bugs on the Rust side still. And also to be more systematic in how we explore and check for weak memory bugs by using model checking techniques. I should also mention that Miri is a team effort. There are 6 authors on this paper which are kind of the main contributors to Miri, but Miri has been developed over many, many years as an open source project as part of the official Rust project. So we received numerous contributions from many, many people that I cannot even all fit on one slide. And it's thanks to all of them that Miri has become the practical tool that it is. So with that, I thank you for your attention. Miri is a practical UB tester for Rust. This is the URL where you can learn more about it. And if you want to install it, it is a Rust up component. So as a Rust user, it is very easy to install. And so now with Miri, I hope you can all help us keep the Kraken at bay and protect Ferris from this deep sea monster. Thanks.
Okay, thanks, Ralph, for the presentation. So we will take now questions.
Thank you for the nice talk. On slide 20, you had like something that looked like a theorem. Before this, Miri can detect all de facto UB and deterministic Rust programs. That looks like a theorem. Did you prove this, or how do you ensure this even?
It's more of a definition, isn't it, right? Because as a theorem, we would need a specification for what the UB in a Rust program is.
So de facto UB basically means that Miri can detect it. So hence it holds by definition.
Well, no, de facto UB is defined by whatever the compiler does. So, I mean, if this is a theorem, then the theorem statement includes 10 million lines of LLVM source code. So no, we did not prove that theorem.
But how did you figure out what the compiler is doing exactly, apart from just talking to a whole bunch of people?
By talking to a whole bunch of people and staring at the source code a lot.
Okay, but that might be incomplete. So
Yes.
there might actually be still...
I mean, Miri is a tool, it might have bugs, yes.
But it might also be that after talking to a lot of people, you somehow misunderstood or missed out on something. So there is still more UB that, de facto UB that you don't detect.
That's possible. That would, in many cases, be considered a compiler bug because, like, we have documentation in Rust on what we currently think is UB, and so if we had to add more things to that, that would be something that, like, typically in Rust we would say, no, actually this is supposed to behave like that. So it's hard to exclude that, right? This is practical work. This is not. There's no foundation in the theory for this. But if there are cases like that, it would be a discussion whether we consider this a compiler bug or this is actually be in the language and programmers have to avoid it.
I see, it makes sense.
Thanks for the talk. That was very interesting. I had a question about the non-determinism, and so it seems that it's kind of stochastically resolved at the moment. Like if you have some non-deterministic execution, you just pick one randomly, maybe you pick a couple randomly. I was curious why you don't, or maybe you have considered doing like a complete search. Is it possible to do a complete search? Could we do some kind of breadth first search over interleavings so that we can get some completeness result for this de facto specification?
The primary source of non-determinism outside of concurrency is the addresses of new allocations, where there are 2 to the 64 possible choices. So doing anything exhaustive is completely out of the question. You would actually need symbolic techniques or something like that to get any kind of completeness there, and that would mean rewriting everything from scratch.
Right, yeah, so that was actually my original question was about the address space, because I was going to assume that you don't model it directly, but...
We do model it directly, but we just, I mean, if we only pick one execution, we can basically go and pick an address at random.
Right, okay.
We don't quite do that. We do something which we hope is more likely to find executions where there are bugs.
Yeah.
But yes.
Okay, so have you considered using symbolic address spaces?
Considered, yes, but it would mean rewriting everything from scratch.
Okay.
So,
all right, thank you.
I would like to ask about UB. So you did some work with compiler team, obviously, to extract this knowledge about known UB. Have you thought about systematizing this knowledge, maybe extracting it, maybe formalizing with some DSL within Miri? So there will be like first steps toward like systematic definition of UBs in Rust?
Yes, that's ongoing work.
Thank you for the great talk and the great work. I was wondering how much of this work can be transferred to other languages, and which languages do you think can benefit from this kind of approach?
Yeah, thanks. So, I mean, most languages don't really need this because they don't have UB, so that's nice. Though I guess even OCaml, if you use object.magic, you can have notions of UB. So then what you would need is a good enough understanding of what is and isn't UB. Right? So, I mean, C and C++ are the obvious candidates for something like this. There are tons of tools which go in the direction of this. There are sanitizers like UBSAM and address sanitizer and so on. There's valgrind. None of those can actually claim to catch all of the UB in C, but they can catch many of it. So that's a good start. So to do the exact same thing in C, well, you need a full understanding of all of the undefined behavior in C. And it's kind of your choice whether you do this according to the C standard, which is full of ambiguities, or according to what compilers really do, which is, well, I mean, those are big software projects, right? You would need to spend a lot of effort analyzing that. But definitely possible. It's harder in C, because C has more non-determinism and more UB than Rust. So you would have to spend a lot more effort. I'm not aware of any free tool doing that. There is a company that has a product that claims to be able to do that. I couldn't check what they're doing, so... right, but I mean, that's not a practical bug finding tool, right? Like you can use it on small examples, but if your code has 100 lines, you're not going to get very far.
Okay, thank you. I think we have to move to the next presentation now. So thanks a lot again, Ralph, for the questions. Sorry, we stopped it. No, great tools. Okay, good. So please.
Very similar way. In fact, this is very. We're doing exactly in the article.
HDMI.
We're doing something else. We'd like to do it for all of C++.
Yeah, I've seen some of it. So far, I think there's a lot, like, to actually cover all the UB.
Oh, yes.
But
there's more missing than the coverage, but we have the framework.
Yes.
In 29, we'll have the framework.
Yeah, so that's great. Love to chat more if you want.
Sorry, we are going to move to. Okay, so we are now going to start the last presentation of the session, which is about piecewise analysis of probabilistic programs via k-induction, and the talk will be given by Tangshu Niran.
Okay, hello everyone. Welcome to my talk. I'm Teng Shun, and in this talk, I will introduce our recent work on probabilistic programs. This work was conducted with my co-authors, Shenhua, Hongfei, Naijun, Jingyu, and Shiyang. So let's begin with the background of the probabilistic programs. This is the syntax of the probabilistic programs that considered in our work. So probabilistic programs, these kinds of probabilistic programs enrich the imperative language with these two special statements. The first one is that we sample a value from a given distribution, and the second one means that we execute the lab statements with probability p and execute another one with probability 1 minus p. And our focus is the quantitative analysis of probabilistic programs. Compared to the formal analysis of classical programs that focus on the qualitative properties, the formal analysis of probabilistic programs may concern more on the quantitative properties in many situations. For example, the expectations, the assertions, properties, and expected running time, and so on. And usually, they try to reason about the expected value of some quantitative properties after the programming terminates, and they try to derive the tight numerical bounds. In the literature, most previous work consider the monolithic bounds. For example, the synthesis of invariance or sub-invariance, and they try and expectation analysis and termination analysis and so on. But unfortunately, the monolithic bounds are too conservative or complex, and sometimes they do not exist at all. Recently, several works try to consider to synthesize the possibly piecewise bound to verify the input bound. These two works are listed here. One is the Takas paper that based on the counterexample guided, and another one is based on the data-driven learning methods. So in our work, our target is to synthesize the piecewise polynomial bounds. But there are two main challenges in our work. The first one is that how can we partition the state space into several parts, which corresponds to the piecewise the concept here. And the second challenge is that how can we design efficient algorithm to derive these kinds of bounds. The main idea of our work is that we apply the k-induction principle and design the corresponding algorithm to solve this problem. The intuition here is that the partition of the input domains is quite closely related to the loop exist iteration bound, iteration codes, which corresponds to the k-induction unloading of the loop and the parameter k's in the k-induction principle. So formally, the problems that we concerned in this work can be described as follows. Given a probabilistic while loop P and a return function F, which correspond to the quantitative property, we try to synthesize tight piecewise bounds on the expected value of F after the program terminates. Our contribution lies on the following two aspects. The first one is the theoretical foundations. We show how to extract piecewise information from the k-induction operators. And the second is that we utilize the extending OST optional stopping theorism to ensure the soundness. For the algorithms, we propose efficient and sound methods to deriving the constraints. And second, we design novel algorithms for when solving the constraints. It was split into two cases, the linear case and the polynomial case. So first, we will introduce our theories. Let's begin with the K-induction, the introduction of the K-induction. So for the K-inductions, the definition is that given a monotone operator phi, the upper K-induction operator is defined by the functions phi that map element v here to the mid operation between the phi of v and a given element u. And you can see that the element u is attached at the bottom of that operator phi. And the lower K-induction operator is defined similarly by replacing the mid operation by the joint operation. So we have the following inductive theorems, this one, which build the relations between the K-induction and the one induction. The left one is the K-induction and the right one is the one induction. And we call the left expression as the upper K-induction condition on the lattice. So this guide us intuitions that maybe we can find the element u that satisfies the K-induction there, and the expression, these expressions, the middle of the expressions, it would be the piecewise upper bound that we want. So based on the theory that we introduced, we can initial the K-inductions in the probabilistic programs. PP is the short for probabilistic programs. We define the following concepts. The first one is the pre-expectation, which corresponds to the expected value of the function g after the execution of the queue. And the second concept is the characteristic functions, which correspond to the monotone operator phi that was defined on the last page. Informally, the characteristic functions outputs the function f if the loop guard is violated, and otherwise it will output the expected value of g after the execution of the loop body. So based on the theories introduced above, we can define the upper K inductions in probabilistic programs as follows. The left one is the upper K induction operator, and the right one is the upper K induction conditions in probabilistic programs. And we have the similar intuitions that was introduced on the last page. Maybe we can find some function h that satisfy the K induction here, and the function under the operation of the phi, like this one, it would be the piecewise upper bound that we want. So the next step is that we need to answer whether this distribution is correct. So the answer is yes. We propose the soundness theorism for the linear case and for the linear programs and the polynomial programs. The main idea is that we try to find some general conditions like the first one and the second one, and combine with the upper or the lower K induction conditions. Then we prove that it satisfies the condition of the extended optional stopping theories, and that was proposed in the POPL'26 paper. And we utilize this extended OST to prove that the soundness of our theories so you can see that for the linear and the polynomial programs. And okay, so far we have completed the challenge, the theory challenge that we have mentioned. So the second thing is that we need to design the algorithm for our theory. I will introduce our algorithm with this simple example. This simple example models a very simple random walk. The step size x is increased by 1 in each iteration. The step size x is increased by 1 with 50% probability and was set to -1 with the other half probability. And our target is to reason about the expected value of y after the program terminates. First of all, we try the conventional methods, that is the one inductions, to derive some monolithic bounds. But unfortunately, the monolithic linear upper bounds do not exist. And for the polynomial bounds, they are much more conservative. Well, with our methods, we can derive the following piecewise bounds, which in fact is the exact results. Our approach has the following 4 steps. We first set up the polynomial template edge and do some pre-processing, including the invariance, the hyperparameters, and so on. And in the third step, we need to derive the k-induction constraints like these ones that I have mentioned on the former pages. And the last step is the polynomial solving. Since in these k-induction conditions, they have several pointwise minimum operators, which makes this constraint is very complicated and conveyed. So these 2 latter steps are non-trivial and need some new algorithm to address it. For the third step, we propose, for the third step, I mentioned that our target is to transform the original k-induction constraints into these simpler forms. And as you can see, that the minimum operator appears at the outermost of the left-hand side of the inequalities. And each function here, each edge function here do not contain any minimum operator. We propose our algorithms to achieve these transformations. From the initial symbolic states, we unfold the loop once. We unfold the loop and make decisions at each program states that we met during the unfolding process. And we can choose to unfold the loop once more or choose to stop unrolling. And the third action is that the unrolling is forced to stop because the number of the unfolding has reached k, and k here is the parameter of the k-induction. Each strategy is composed of each decision decides a unique loop-free programs, and we show that each function here, each function here uniquely corresponds to the pre-expectation of each loop programs. Maybe this description is a little difficult to understand, so I show you with an illustrative example. And in this example, in the loop body, with probability p, you will execute the first statement, and with probability 1 minus p, you will execute the second statement. And from the initial states, we unfold the programs once, and on these 2 leaf nodes, we choose not to unroll the loop once more. So we obtain the first case. And we can change the decision here, and we unfold the programs. We unfold the loop once more, and we obtain this case 2. The case 3 is similar with the case 2 that we exchange the decision performed on these 2 leaf nodes. And the case 4 is quite easier to understand. That is the way choose to unfold the loop on these 2 leaf nodes, and we obtain the full tree here. And as you can see, is that the maximum envelope process, the number here is 2, and which corresponds to the 2 induction here. So that's all the cases. That's all the cases that performed our algorithm, and we can show that when applying 2 induction on this example, we can obtain simpler forms that minimize H1, H2, H3, H4, and each H function corresponds to the pre-expectation of the loop-free programs in each case. Okay, after that, so far we have derived the k-induction constraint like this form, and each function, H function here is a piecewise function. And we transform this constraint into a canonical forms like this one, and each B here, each Bi here is the predicates. And the expression Eij here is the monolithic expression without the piecewise informations. And in this example, we can obtain the canonical form in these forms. And as you can see, that the whole state space is divided into 2 spaces. First one is the x is smaller than 0, and the second part is that x is no smaller than 0, which corresponds to the piecewise concept here. And the final step is the constraint solving. And we have obtained these canonical forms. The step is operated as follows. We transform these kinds of constraints into this expression is unsatisfiable. Note that this transformation is equivalent. And then we consider a variance of Motzkin transposition theories, which will equivalently transform the former one to the lower one. And then we call the bilinear solver to solve this constraint. This is for the linear case. And for the polynomial case, we need to try something relaxations that will relax the original canonical forms into the convex combination forms. So in these forms, the soundness is guaranteed by the following fact, that if the result satisfies the relaxed constraints, it will satisfy the original canonical forms. And then we apply the Pulina theorism and transform the original problems into the SDP problem, and we can use some state-of-art SDP solver to solve the original problem. To summarize, there are several key sides of our template algorithm. First, we establish the polynomial templates, and the second step, we derive k-induction condition constraints with our new algorithms. Then we transform into a canonical forms, and the final step is that we do the polynomial solving, especially for the linear case and the polynomial case. Next, we perform some experimental results. We want to answer the following 3 questions. The first one is that how effective is our approach in generating piecewise bonds? The second question is that how does our approach compare to the most closely related methods? And these 2 tools were listed in the former pages. It's the Takas paper and the Cave paper. And the last question is that how do our piecewise bonds compare to the higher degrees monolithic polynomial bonds? Okay, so we show the part of the experimental results, especially upper bounds in here. To answer the question 1, for the linear case, that our methods can synthesize tight piecewise bonds on the benchmark with a few minutes. And on some of the benchmarks, we can obtain the exact results. And for the question 2, our answer is that other tools fail on about 40% of benchmarks. And on the benchmarks that all the methods can get generate results, our results are comparable. And about the question 3, it shows that on most of our benchmarks, our piecewise results are significantly tighter and more concise when the monolithic bonds. There are 2 evaluations here. The first one is the PCT, and the second one is the difference. The PCT stands for the percentage of the error that our bonds are not better than the monolithic ones. And the difference, and the column difference here shows that how's the difference between these 2 kinds of bonds. A positive value shows how much our piecewise bonds are tighter than the monolithic bond. And for the polynomial case, for the question 1, our approach can derive piecewise bonds on most benchmarks within seconds. The percentage here is about 80%. And for the question 2, that compared to the tool exists, we can handle more benchmarks and our methods are more efficient. For the question 3, is that we show that our piecewise bonds are tighter and simpler than the monolithic bonds. In summary, our focus is the piecewise expectation analysis in our work. And we try to synthesize the tight bonds for the polynomial, for the probabilistic while loops. And our theoretical foundation lies on the combination of K-induction principle and optional solving theories. And we design for the implementation, we design the novel algorithm for polynomial solving. For the future work, we focus on more efficient polynomial solving, and we will emphasize on the scalability problem. That's all. Thank you.
Okay, so we have time for a few questions. David?
Using nonlinear solvers such as semi-definite programming is usually fairly difficult. I mean, these solvers are brittle. Sometimes they fail to give a result, or they give a result that is slightly outside of the domain, or things like that. Have you had to do phases for repairing the results of these solvers or anything like that?
So you mean that the numerical solver?
Yeah, the output of the numerical solver, it's usually not very nice, and also sometimes it's slightly wrong.
So further thing is that I didn't mention in my slides that we also perform the numerical repairs to the numerical results. And the second thing is that if the result is not very well to perform this repair, we check the correctness. We check the correctness of the numerical results.
In your evaluation, the question 2, you say that the tool fails on many examples, and I wonder if it is because the tool is not precise enough, or is it because there is no solution of the form that you are looking for?
You mean the table 1? In this table, correct?
Yes, or the next one.
Yes, the symbol here means that we can obtain any monolithic linear bonds through the conventional methods. That is the one induction. Since the numerical solvers outputs is invisible, so we can obtain any result from this method.
So I also have one question. I mean, you said your piecewise property or piecewise bound is driven driven by the K induction. So what I'm interested in is how can your algorithms decide which piece? How should you should split state space into pieces,
Yeah.
And then you said that's driven by the K induction.
Yeah.
And then that makes me feel, I think that maybe that's related to the loop condition together with how many times I go through the loop. Is
Yeah.
that the right intuitions or your
Yeah,
methodology
it's the right
discovered?
intuition.
Okay.
Yes.
So actually, I had a question maybe a little bit related to Hong Sok's last question. So in fact, K induction, if you look at it from a static analysis perspective, is a little bit like injective some very specific kind of sensitivity to context. Did you do other kinds of sensitivity make sense? Like you unroll the loop in a very specific way. Would other ways also help getting accurate results?
I think makes sense.
So I guess my question is, did you look at other ways and find why this one works better?
Okay. Sorry. Can you repeat again?
Okay. So my question is, if you look at K induction from a static analysis perspective, you unroll the loop a number of times, and then you have to find a strategy to decide how to unroll, like Hong Sok asked. There are many other ways to do some kind of program sensitivity in the program execution context sensitivity in static analysis, where you try to be sensitive to the point, to the trace that brings you to a program point. This is just one. So my question was, did you try to consider others and find out why this one works better in your setup?
I think that your intuition is correct. Yeah.
Okay. Well. Any other question? Okay, so then we can thank you again.
Thank you.
And this closes the session, so thanks a lot.
I don't have to do anything, basically. Okay. Maybe we can start. So welcome everybody to the session on quantum programming languages. So the first talk will be given by Bonan Su on an expressive assertion language for quantum programs.
Okay, thanks for the introduction. Good afternoon, everyone. I'm Bonan Su from Tsinghua University, and it's a great honor and pleasure to present our recent work on the expressiveness of an assertion language for quantum programs. And this is a joint work with Professors Feng, Ying, and Zhou. Okay. Although I may assume that most attendees to the quantum session and POPL conference are already quite familiar with quantum programming, I will still spend several minutes recapitulating the necessary backgrounds, including the formal definitions of these jargon terms, because I need to clarify the meaning. Is there a mic? I need to clarify the meaning of the expressiveness problem we have solved in this work, which can somehow be regarded as a small but very theoretical and fundamental problem. And then I will present the assertion language we designed, and finally, if time permits, I will have a brief overview of the technical proofs of the expressiveness, which is quite tedious, actually. And so in this work, we are studying a wide acknowledged prototype quantum language named QWHILE, and the syntax of it is presented here, and we use a calligraphic letter E to denote a primitive quantum channel from a fixed set. For example, you may include unitary transformations drawn from a specific universal gate set. And we use the calligraphy letter M to denote a binary quantum merriment, which means the merriment has only two outcomes, true or false, and different branches in the if statement or the while loops, the loop body of the while loops may be executed depending on the merriment outcomes you obtain. Okay? So the denotational semantics of a program statement is associated with a quantum operation, which is denoted by S with double brackets. And such an operation is defined by induction on the structure of the program statement S. And you may notice that, okay, the calligraphy letter I here denotes the identity operation. And in the semantics of if branching and while loops, we use calligraphic letter T and F to denote the operation when obtaining the corresponding outcomes true or false in the guard merriment. Okay. Since we have encoded the probability of outcomes as the trace of the program state, because you may see that the quantum operation here is not divided by the trace of the post-merriment quantum states. So we need to sum up the program states of the two branches to obtain the final program state for the if branching statement. And this is quite similar to the case in probabilistic programs, but quite different from the classical programming. Okay? And it is similar for while loops, except for that the semantics of while loops involves an infinite summation, which can be proved to converge all the time. And as we will discuss later, such an infinity poses significant challenges in the establishment of the weakest precondition. Okay. So next we will step into the program specification. And essentially we use a Hoare-style triple PSQ to specify the property of a program S, and where P, Q are commonly referred to as the precondition and the postcondition, both of which are quantum predicates formally defined as a Hermitian operator with eigenvalues bounded between 0 and 1, and S is a QWHILE program statement as defined before. And the validity of such a triple indicates that the expectation of marrying the precondition P on an arbitrary initial state rho is no larger than the expectation of the postcondition Q on the resulting state after executing S. Okay, is such an inequality. And similarly, we can define an order between quantum predicates, such as, and this order can be intuitively understood as an analogy to the logical entailment in classical logics, such as P implies Q if and only if Q minus P is positive semi-definite. So given the program specifications and the order, we can now formally define the notion of weakest precondition as the valid precondition, which is weakest with respect to the lower order. Okay? So it is actually a theorem that the weakest precondition always exists, as you can obtain the weakest precondition by applying the adjoint operation of the semantic function to the postcondition Q. The proof is actually very simple by the Schrodinger-Heisenberg duality, which has been discussed at a presentation in Plan QC session the day before yesterday, if I remember correctly. Okay. And so a direct corollary is that the quantum weakest precondition calculus is complete from an extensional perspective. it is complete because the wicked precondition always exists, as the theorem suggests. But I will soon illustrate what does it mean from an extensional perspective. But before that, I need to introduce the notion of assertion language. I know there are various definitions of language, the jargon term, in different fields, such as the automata theory or something. But here, by a language, we mean a collection of formulas that are generated by at most countably primitive symbols and finitely many grammar rules. And a language is referred to as an assertion language if it is used to express preconditions and postconditions. For example, in classical programs, we use first-order arithmetic logic as the assertion language. They are formulas involving only finitely many quantifications, arithmetic operations, and natural numbers as constant symbols, because natural numbers are the set of which is countable. Okay? And the set of variables should also be countable. And now we see something is from an extensional perspective, means we treat the precondition and postconditions as purely mathematical objects, such as the Hermitian operators we just discussed before. But from an intentional perspective, we need to express the precondition and the postcondition as formulas within an assertion language, for example, the first-order logic. Okay? So here is a table comparing the extensional and intentional assertions across different settings. And in classical programs, it is a common practice to adopt the first-order arithmetic logic. For example, the formula here exists y, such as x equals 2 times y, describes a program state such that the assignment of x is an even number. And each predicate formula can be then interpreted as a set of program states satisfying the predicate formula, of course, but not vice versa, because not all such sets of program states can be expressed by a predicate formula due to the inherent computability limitation of first-order logic. So every intentional formulas can be interpreted as extensional objects, but not vice versa. And similarly, in probabilistic programs, it was Conan who first generalized satisfy or not predicates to measurable functions on program states. And a recent work presented on POPL'26 designed an assertion language for such measurable functions. And for quantum programs, as we formally defined before, quantum predicates are defined as Hermitian operators. And in this work, we design an assertion language to express such quantum predicates. Okay? And then a question on expressiveness arises naturally. Is there a non-trivial assertion language for quantum programs such that the weakest precondition always exists and can be expressed as a formula within the language? Of course, we may assume that the post condition is formulable. Okay, so we put a further constraint here. We require the WP to be expressible instead of just the existence of the WP. And the answer is yes, and in this work, the core contribution is that we provide such an assertion language for quantum programs and proved its expressiveness. Okay. Okay, so next I will present our assertion language, and the syntax of it is presented here. And you may notice that the first two lines define the arithmetic and the Boolean expressions in classical propositional logic. And you may notice that we only include rational numbers as constant symbols because the collection of rationals is a countable set. Okay? Only countable set can be stored and manipulated on a practical computer. Okay? And the third line defines the coefficient formulas where a lot of special constructs are included. For example, the indicator function, which is denoted by a Boolean expression B with bracket. And such an expression evaluates to 1 if the Boolean expression is satisfied, or evaluates to 0 otherwise. And similarly, we support the supremum and the infimum over classical variables. And you may notice that the production between two coefficient formulas are not accepted as valid formulas. But we will discuss later that actually the alpha times beta can be expressed as a coefficient formula, provided that alpha beta are bounded below or something. Okay? Actually, the first three lines defines exactly the same assertion language for probabilistic programs presented at POPL 2021. And for quantum parts, we are expressing quantum predicates, that is Hermitian operators, as linear combinations of generalized Pauli operators with coefficients expressed as the coefficient formulas defined before. Okay? That is our assertion language, quite simple, right? But actually, the proof of its expressiveness is very tricky and tedious. And next, okay, here is a concrete example. So you may see that the expression on the left, right is interpreted on the operation on the right. And here, the component surrounded by a blue box evaluates to x if the Boolean expression is satisfied, that is 2 times squared x less than 1, or evaluates to 0 otherwise. So taking supremum over all possible x can express an irrational number with square roots. Okay, it's quite straightforward to represent irrational numbers with the combinations of supremum, infimum, and indicator functions, and that's the trick. So next, we will step into the most challenging part, is the proof of expressiveness. And honestly speaking, the problem here is inherently tricky and tedious, so I will try my best to get across the primary intuitive ideas behind them, and I will omit many technical assumptions and details here, okay? Overall, the proof is constructive, which means we provide explicit construction of the weakest precondition for every program statement and the general postcondition per se, okay? And since the weakest preconditions for program statements other than the while loops are more straightforward and can be obtained by directly extending classical techniques, we will put a particular focus on the construction for the weakest preconditions of the while loop. When we first recall that from an extensional perspective, the weakest precondition of while loops can be obtained by applying the adjoint operation of the semantics function to the postcondition Q, which can be written in an expression including limit, summation, and unfold composition of a quantum operation, which is quite complicated, okay? So the first problem we need to address is that it seems infeasible to express the application of an unfold composition of a quantum operation to Q as a formula parameterized by n, okay? So the first thing we do is to reformulate the weakest precondition for while loops. And since Pauli operators form an orthonormal basis, so we can decompose the postcondition Q in the basis of a Pauli operators with coefficients being the inner products between Q and P. And the angle bracket here denotes the inner product. So the application of E on Q can actually be expressed as an expression, can be expressed as a linear combination of EQ with coefficients being the inner products. And similarly, for a composition of two quantum operations, it can actually be expressed as linear combination of one-time application of E to Q with coefficients being the product between scalars, because inner products are scalars, okay? So we have eliminated the composition of quantum operations, but we introduce inner products and summations. And in general, the unfold composition of a quantum operation can actually be reformulated in an expression with summation and inner products and a summation of n terms. Okay. So we will next study how to express these weird expressions, such as the summation, the production, the inner product or something, and the limit. Don't forget about that. And the first thing is that, the first theorem we present is that the summation and production can actually be expressed as coefficient formulas. The theorem states that for an arbitrary coefficient formula alpha x, where x is a free variable, such a formula actually represents a series. For example, in the below, alpha x equals x means represents a series 1, 2, 3, 4, since alpha 1 equals 1, alpha 2 equals 2, and so on. And for such a coefficient formula alpha x, if alpha x is bounded below, we claim that there exists coefficient formulas sum alpha xn equals to the summation of alpha I over I from 1 to n. And the similar results hold for production. For example, if alpha x equals x, which means it represents a sequence 1, 2, 3, 4, 5. So the summation of the n items is expressed in the formula n times n plus 1 over 2, which is universally known as the Gaussian summation formula. Okay? But in general, such a construction we need to use Gödelization. I will speak in a very intuitive fashion, and I may omit several details. We use Gödelizations to encode a finite sequence of rational numbers. And we take supremum of such rational numbers when the rational numbers are strictly less than the alpha I. So we use Gödelizations to encode the rational numbers and then take supremum of such rational numbers to obtain the desired value, because we're approximating the summation of the series from below by rationals, and the rational numbers are dense in reals. So the supremum is equivalent to the summation as we desired. Okay? And next, we need to express the inner product between two predicate formulas, that is linear combinations of Pauli operators. And this can be achieved by substitution. Because Pauli operators forms an orthonormal basis, then the inner product between the two summation actually equals to the summation of the product between the corresponding coefficient. And this can be seen as substituting each occurrence of pi in the first expression by the corresponding coefficient bi in the second expression. Okay, this is a kind of substitution, and we are substituting Pauli operators by coefficients. Okay? And here we may need to express the production between coefficient formulas, and this can be achieved by constructing a new coefficient formula, gamma x, such that the gamma x evaluates to alpha if x equals 1, and it evaluates to beta if x equals 2, because this is the definition of indicator functions. So by the previous theorem, we just take product alpha x2, we just obtain the same value as the alpha times beta. Okay? Of course, everything here is bounded, and I may omit the tedious discussion about. And finally, we can express the limit with the help of sub and inf. And for example, if you have a converging series represented by alpha x, you can first take infimum over uppercase n, and then take the supremum over the lowercase n. And with the help of indicator function, you can claim the lowercase n is larger than the uppercase n. So after you're taking the supremum and infimum in turn, you will get the desired value, the same as the limit. Okay? Of course, in this case, we need the alpha x to be non-negative, but in general case, we can actually show that the limit in the Wiki-zip condition for while loops can be expressed with the help of sub and inf in our session language. So we're now putting them together, and from an extensional perspective, we have the formulation and expression of the Wiki-zip condition for while loops. And now, actually, we can claim that the the weak condition can be expressed as the linear combinations of Pauli operators with coefficients being expressed as the coefficient formulas in our assertion language. So actually, the most tricks here are classical and have nothing to do with quantum parts. Okay, and you may notice that there are limits, there are summations, there are inner products, and we have discussed before they can be expressed. And it is worth noting that you may see that there is still one-time application of quantum operation E to each Pauli operator Pi. And such an E dagger P is expressible by induction. Why? Because actually the quantum operation E here is connected with the semantics function of the loop body or the merriment in the while statement. So we can prove by induction hypothesis that the E dagger P exists, because it's a common practice to assume that the weak condition for the loop body and the merriment have already exist. And given the existence of the weak condition for wild body, for loop bodies, we then construct the weak condition for the whole while loops. Okay? So very loosely speaking, we have complete our proof of the expressiveness. And so the conclusion is that we have designed a assertion language that is expressive for quantum programs. And a very direct corollary is that the weakest precondition calculus for quantum programs is complete from an intentional perspective. And since as far as I know, maybe our work is the first to present the intentional completeness results. Okay, it's a very elegant and concise theoretical result. Okay, and as an application, we have developed a sound and relatively complete quantum Hall logic. And it is complete because there is an equivalence between the existence of loop invariant and the existence of the weakest precondition for while loops. So the relative completeness can be directly derived from the expressiveness of the assertion language. And now we are taking our assertion language to express the precondition and postconditions in Hall triples. And okay, that's all. Maybe I'm talking too fast, and thank you. Any questions?
There is a question over there.
Hi, very nice talk. As far as I understand, this is based off of expectation satisfiability, which is the trace of the pre and post conditions. How do all these change when you consider complete satisfaction of projections, where a very analogy is the applied QHL versus the normal QHL? So how would projective satisfaction fit into all of this?
Oh, thank you for your excellent or valuable questions. And actually, the history that I first considered the completeness from satisfaction or not based, which is also referred to as a predicate-based completeness. And then I come to the expectation-based reasoning. But as we all know that the Hall logic, an elegant inference system for Hall logic, only exists for expectation-based reasoning. I don't know whether, because you can hardly derive a complete inference rule about the if branching in a predicate-based manner. Of course, that is for the certified or not based, but you mentioned the projection-based ones. I haven't considered about it clearly, and I'm trying to, at the future work maybe, because it's quite difficult to design such a language for projection, actually. You need to encode the coefficient or something. Thank you.
Thank you. Please, Robert.
So there have been a lot of proofs done using the original QHL and a bunch of its derivatives. And I'm wondering both if you've tried to do the same proofs and kind of how they compare just in terms of usability of the new logic, and also whether or not the sort of the nice syntactic structure of this logic makes it easier to mechanize.
Sorry, background please. I can hardly grasp which is our question.
So just in practice, is this as usable as proving things, or is it just sort of complete in theory but harder to use? And also, can you mechanize it?
Oh, that's a very critical but valuable question. And actually, the motivation for designing an assertion language is for the purpose of practical usage. But actually, as far as I'm concerned, and I know that most assertion languages, except for the first order language for the classical programs, the assertion language for probabilistic or quantum programs language are often categorized in two classes. One is specially designed for practical purpose, such as the path-thumb or something. And another class is designed for theoretical results, such as our work or the work on at POPL 2021. And we can hardly achieve both for now. Okay.
So it's future work.
Maybe. Thank you.
We are running out of time. Sorry. Maybe we can keep it. Yeah, because
we can talk in person later. Thank you.
Keep it offline. So let's go to the next. And the third talk of the session will be given by Jennifer Bacon on qubit quantum programming with projective Cliffords.
Great. Okay, microphone's on. Okay, yeah, thank you. So I am going to talk about sort of a different perspective on quantum programming. Normally, in the usual model, we're thinking about unitaries as transformations on states, right? So it takes a state to another state. But I claim that in some cases, it's actually going to be more useful to describe a unitary by its conjugation action on the multi-qubit polygroup. So this polygroup is the unitaries that are generated by X, Y, and Z. And in fact, any one of them can be written as a combination from the other two. So really, we only need to consider two of these, like X and Z, in some senses. Okay, so this is especially true for Clifford operators, which are exactly the unitaries that preserve the polygroup under conjugation. So the Clifford operators are the ones that when you look at their conjugation action, the result, UP, U dagger, is also a poly operator. Okay. Furthermore, any two Cliffords with the same projective action, actually any two unitaries, I should also say, yes, this is the same Clifford group as those generated by the Clifford gates, like Hadamard, phase gate, and C0. So I will note that any two Cliffords with the same projective action, in fact, this is really true of any two unitaries with the same projective action, are indistinguishable up to global phase. So we can really consider the equivalence class of those unitaries up to conjugation. And in this case, we're going to call that the projective Clifford operators. So rather than thinking about unitaries as a map from states to states, in this talk, we're going to be thinking about projective Cliffords as a map from polys to polys. Okay. So as a programming language theorist, when I started thinking about Cliffords this way, I said, oh, okay, well, let's build a language where we can write functions we can write functions over the poly group, and well-typed functions should correspond to projective Cliffords. Turns out that there's some details we need to work out in order to make that happen, but it does in fact work. So we call this language in the paper lambda PC for projective Clifford. I would like some properties to hold of this language. I'd like this to be a pure lambda calculus with a well-defined operational semantics. I would like these functions, these well-typed functions, to still be able to be compiled to circuits. I'd like to be able to run them. And I would ideally like this language to enable new ways of thinking about quantum algorithms. So by sort of changing our perspective and how we program these systems, we will hopefully be able to build new kinds of algorithms, or at least think about algorithms in a different way. Okay. So this middle part, the compilation to circuits, sounds quite hard, but it isn't. Or at least it's understood very well, so it's all worked out. So So this is using the same ideas as poly tableaus, if you've seen those. Basically, the idea is the following. So every poly can be written in the following form. I'm going to write a power of I followed by a bunch of x's and z's. So for, if this is an n qubit poly, it's going to have like possibly an x at qubit 1, possibly a z at qubit 1, and so on for every qubit. And so the power of the xi, zi is, those are going to be just bits, right? And this works because y is, I'm writing this with this star operator, it's x star z. And so, any single qubit poly is either identity x, z, or y. Okay, great. So this is like a little bit valued encoding of the polys. I will also note that projective Cliffords distribute over this star operator. And so as a result, we can express projective Cliffords in the following way. So all we need to do is say, what does the projective Clifford do to x1? What does it do to z1? What does it do to x2? What does it do to z2, et cetera? Okay? And so we can kind of list this out in this chart. This chart has 2n entries. And often you'll see poly tableau written out actually as like bit encodings. Okay, so this is an efficient representation of projective Cliffords, right? It's like the size is on the order of n squared. And in fact, it also enables efficient simulation of Clifford circuits. Side note, Cliffords are not universal for quantum computing. Important to note, but they're still extremely relevant for all sorts of different applications. So like including but not limited to quantum error correction. That's a really big source where thinking about Cliffords and thinking about them in this framework as maps on the poly group is in fact a very natural way of working with or building error correcting codes. So as a result, there has been a lot of research and interest into this efficient simulation of stabilizer circuits, as well as efficient synthesis into Clifford circuits. And in fact, these synthesis techniques are like among the best synthesis techniques for circuits. So you see them a lot in optimization techniques. Okay. I will note, however, that these tableaus are data structures. Like they're not really programmable. They're not really compositional. And so we need to do a little bit of work in order to figure out how to really program them. Okay. But before we talk about that, I want to go through a few examples. So let's think about the Hadamard operation as a projective Clifford. So this is the usual Hadamard unitary, right? And we can tell that it's Clifford because if you compute out what it does to x and to z, we can see that we still get polys at the end. It sends x to z and z to x. Okay, well, here's how we would write that in lambda PC. So here we have a function from poly to poly. So when I write poly in this type, I'm referring to a single qubit poly. And then if I have multiple qubits, I'll have poly tensor poly or something like that. Okay. I'm distinguishing the type of projective Cliffords using these bars in the type. So it's like a bar and then a type, lolly, other type. I'm also using these bars to distinguish the sort of pattern matching syntax within the projective Clifford. So I want to say, so I'm saying like, okay, so if the input is an x, then send it to z. If the input is a z, send it to x. And this is sort of like a Haskell style pattern matching syntax. In the paper, we have a core calculus, which uses a case statement. So this is just syntactic sugar. Okay. So now that we've written this function, we should be able to apply it to any poly in the single pivot poly group. So let's see what happens when we apply it to y. It's going to evaluate as follows. So first of all, it will notice that y can be written as x star z. Then it'll distribute the function over the star. And then it will use the definitions to produce z star x, which it knows is negative y. Okay, let's look at another example. So here we have a 2-qubit gate, the controlled NOT operation. And once again, we can sort of fill out this little table to see what does C naught do to x1, z1, x2, z2. And we can use that to define our projective Clifford. Now, there's not necessarily, so far we can basically just like translate these tableau into pattern matching form, which is maybe not that interesting. But once you have this language, this structure, you can do a lot more things. So here's just one example. We have more examples in the paper, but here's an example of the fact that any poly is also a Clifford. Okay, so I would like to write a function that that takes as input a poly and then lifts it to a projective Clifford. And it's a Clifford because of the following fact. This is a fact of the poly group. Any two polys either commute or anti-commute. So in other words, PQ is plus or minus 1 QP. And that sign, the plus or minus 1, can be easily calculated. It's written omega. And we can actually write it down in the non-projective Clifford fragment of lambda PC. So omega itself is not a projective Clifford, right? It takes in two polys and it returns a sign. But it is a linear transformation. So we can define it by how it acts on the basis elements. So omega will take in xi, xj. So if omega sees xi, xj, well, xi and xj are always going to commute with each other because x commutes with x. So the result should be 0. The same is true for z. Z always commutes with z. For xi, zj, if I is equal to j, then they anti-commute. Otherwise, they commute. And similarly for zi, xj. Okay. So that's the definition of omega. We can now write this poly to Clifford function that takes as input a poly, p. This is of type any type tau, any poly type tau. And then it's a projective Clifford, so it takes in another poly, q. And it returns q. I'm sorry, this is a typo. This right here should be oh, it is a q. Okay, yes. So it returns q with a sign, and that sign is omega of p applied to q. So this syntax with the angle brackets, that's indicating the sign in our syntax. Okay. So we're able to write down these functions, but I'd say there's still work to do because I haven't said anything about the type system. So how do we actually check that one of these functions does correspond to a valid projective Clifford? So what do I want from this type system? So my first question is, when does this function from polys to polys actually correspond to a projective Clifford? So as a function, it needs to be a center-fixing automorphism on the poly group. That doesn't really tell me how to define a type system for that. The type system that I want should be characterized by properties that can be checked efficiently by a type system, and it should be appropriately compositional in some way. Okay. So to figure out how to characterize these functions, I'm going to look at the encodings that we were talking about when we were talking about the poly tableau. So we can think about that encoding as like breaking the projective Clifford down into two parts. So it's going to take as input a poly, delta v, and it's going to return plus or minus delta phi of v, where that function phi is a function of the input poly, so the input vector. And in addition, that plus or minus is also going to be a function of that input vector. Okay, so finding the properties for what this function, the function from polys to polys takes, can be expressed in terms of the properties of mu and phi. Okay, well, what are the properties of mu and phi? Well, it turns out that can be a little bit complex. It sounds unintuitive, but to make it easier to explain those properties, I want to take a jump from qubits to qudits. If you remember, the title of the talk is qudit quantum programming with projective Cliffords. And in fact, the entire system that we have in the paper is generic over qudits. And the reason for that, there can be several motivations, but one of the reasons for that is that it actually guides us how to find these, the properties of these encodings. So, so qubits, right, are a superposition of 0 and 1. Qdits are a superposition of 0 through d minus 1, just like classical dits are 0 through d minus 1. Okay. So the reason why this is relevant is because it turns out that encodings of projective Cliffords for odd dimensions is relatively straightforward. So we can write every projective Clifford in the following form that sends delta v to zeta of mu of v, delta phi v. So here zeta is a primitive dth root of unity, right? So just like previously we had -1, now we have zeta. And so just to be clear, this v is going to be pulled, this is like the vector v, the font is different, but the vector v is going to be pulled from the uppercase set v, which is 2n dits, basically. And the function mu goes from v to a dit, and the function phi goes from v to v. Okay, so what properties do mu and phi have? Well, mu is going to be a linear transformation, phi is going to be a linear transformation, and in addition, phi must be a symplectomorphism. And what that means is that phi respects this symplectic form, which is this function omega that we saw before. So in other words, phi has to respect, like the projective Clifford has to respect the commutivity relations of the polys that it maps. That's the connection there. Okay, so I will claim, and we'll come back to this in a little bit, in just a couple minutes, I claim that these properties can be enforced by a type system and are appropriately compositional. We'll come back to that. Problem though, we may care quite a bit about, not just about qudits of odd dimensions, but for example, qubits, which do not have odd dimension because that has d equals 2. So what happens when we look at these encodings for even dimensions? Unfortunately, it doesn't work out quite as well. You can still build something. You can build a variety of different encodings. But sort of the one that you might come to fairly naturally looks something like this. So it has the same structure as before. But now it's structured a little bit differently. So the vectors v come from some other set v prime, which are dits, but where the dimension is 2d, okay? And then mu takes that v prime to regular dits, and then phi takes v prime to v prime. Furthermore, this mu may or may not be linear. We don't necessarily know what constraints it's going to have. Phi can be linear. We can choose this encoding so that phi is linear. But then it's only a symplectomorphism if mu is linear, but we don't necessarily know what properties mu is going to have. So this is sort of not a way, this is sort of not a way to understand what properties we're going to get here. Okay. So my co-author Sam and I, in some previous work, worked out a different encoding of projective Cliffords, which has some quite nice properties that work out well for this application. Okay. So fact one is that in the condensed encodings, Q-dits are going to be treated uniformly whether D is even or odd. So we don't have, when we're working with these encodings, we don't have to worry about the dimension D. Okay. In this case, we can describe these projective Cliffords as, again, functions from delta B to delta phi of E with this mu coefficient. The only caveat is that this sort of works for delta B being like a basis vector. So delta B has to only be xi and zi. We'll come back to that in a second. Okay, so with that constraint, we get these nice properties again. We have mu goes from V to dits, right? Z mod dz, and phi goes from V to V. So, and again, V is only talking about D, it's not talking about 2D in some cases. Okay, so we have these properties that mu is a linear transformation, phi is a linear transformation, and phi is a symplectomorphism. Great. And the caveat is that, okay, so this is how this function acts on B, and the caveat is that to evaluate this, the projective Clifford on an arbitrary Pauli, delta V, we need some kind of phase correction. So we need a plus or minus 1. And figuring out that phase correction is maybe, it's not linear, it's like maybe not so easy, but we have formulas to work out how to do it. Okay. Okay, so this condensed encoding, this is going to be our structure for our type system. So our type system for projective Cliffords has the following form. And it uses linear types to enforce that property of linearity for both vectors and the phase function phi. It uses a special symplectomorphism check to check that symplectomorphism property. Doing that check in practice could involve a special solver that's a special solver using SMT solvers, or hopefully in the future we'll come up with a better algorithm for doing that check, but it does work. And then those phase adjustment computations are all wrapped up in beta reduction. So as the user, you don't have to worry about what that sign is, what that sign reduces for, because that's all going to happen in evaluation. Okay. So to wrap up, in the paper, we've got a bunch more examples about programming, especially with Q-dits rather than just qubits. We have worked out a case study that describes how you can write error-correcting codes in this framework in quite a straightforward way by describing how they transform the Pauli group. We also give a categorical semantics for those condensed encodings in a way that corresponds to our type system via Curry-Howard. And of course, we give all the details of the type system and operational semantics. Finally, we also build up some additional data structures and talk a little bit more about compiling to circuits. We have some work in progress implementation, which is available on GitHub. And we're also really excited about extensions of the language to things like stabilizer semantics that involves measurement, but also to in general, universal quantum computing in some interesting ways. So I think that's all we have, and I have a couple minutes for questions, I hope.
Yeah, indeed, we have a little bit of time for questions.
Thank you, great talk. I wonder if you attempted a completeness proof, because your poly-tableau formulation looks like a bit like of a saturation, and so I wonder, did you try to prove, like, say, that all the correct programs are well typed?
We do have a completeness proof. Yes, every projective Clifford, or every projective Clifford can be expressed in this language. And that is based on the completeness of the condensed encodings as well. So,
thanks.
Hi, thanks for the talk. You mentioned the, I can't remember the word you gave it, but the thing that checked the symplectic form was checked by an S&T solver. Do you know if this is sort of a decidable fragment of S&T solving? Or more in general, do you know that your type system has decidable type checking?
This should be decidable. It's all in terms of bit vectors.
So it should fall in some decidable fragment of the S&T system. Okay, thank you.
Yep.
Other questions? I was just curious about linearity, because you mentioned linearity at some point. Do you enforce a strong form of linearity, so every function is linear, or do you have things like comonads, which allows you to copy maybe parts of programs that maybe do not refer to qubits?
Yeah, so we have, we do add in the nonlinear variables. So it's not shown in this, but we have like an additional context for nonlinear variables, and only the things of poly type are treated linearly.
Okay.
Yeah.
Okay, let's take the speaker then.
Yeah, thank you.
Great. So the last talk of the session will be given by Kengo Hirata on untangling quantum computing with separation logic.
Does it work? Okay. Yep. So hi. So this talk is about separation logic for quantum computing that can handle entanglement and measurement in a nice way. So why do you care about separation logic in quantum computing? Well, it's because in classical separation logic, it's been widely studied, and it's been shown that it can bring a huge benefit in scalability by enabling a modular reasoning for it. And we want to have a similar effect for quantum computing, so we want to do this. So this is a slide for a quick overview of our work. So before our work, there were some quantum separation logic existing, and they have been inspired by the classical separation logic, and they have introduced frame rule that can represent that enables kind of local reasoning for each disentanglement component. So this is inspired by classical separation logic, but we want to have like more like rich thing, because like quantum computing is more complicated, and we have a lot of phenomena that doesn't occur in classical setting. We want to have some more rich thing, and that's our work. Oops. So the first idea we want to do is that we want to have a reasoning rule that can represent that correspond with superposition. That's the first idea, but it turns out this idea is, in a naive sense, is not compatible with measurement. So we're going to, but we still want to have measurement, so we're going to add something more that can to enable to reason about measurement as well. So that's the big picture of this talk. Okay, let me review the previous work. So in previous work, quantum separation logic, so separation logic is just kind of programming logic. So there, a proposition represents a kind of quantum state. So for example, if you write like x maps to 1, that represents qubit x has state 1. And if you write like in the second line, then this can represent a state of qubits, state of qubits that has the state 1, 0. And we also have Hoare triple, and meaning if you have a precondition, and if you evaluate this NOT gate, then you get this state. And the motivating observation to introduce separation logic is this. So let's say you're given a quantum circuit, which is possibly huge, but let's say you manage to prove the first line. And then later, you realize that you also want to have the second line, which says you also have another qubit y, but this is disentangled. And yeah, let's say you want to have this one. And the first one, it's a way to just prove this is just do the proof again. But you don't actually have to do it, because this should follow automatically. And that's the idea of introducing separation logic. And we want to represents this phenomenon logically. So to do this, separation logic introduces something called separating conjunction that can represent a disentangled state. And with this thing, for example, if you write like psi separating conjunction phi, then this will represent disentangled state like this. And to realize this reasoning, they introduced frame rule. And for example, we can do the same thing as we wanted to do. And the intuitive meaning of this is like, if you want to prove the second line, then you can focus on some disentangled resource, which is local, and then just prove them up, then add the disentangled state later, and to prove this second line. So this is some kind of reasoning rule that allows you to focus on some disentangled component. So I want to call it entanglement local reasoning. So this is cool, and it works. But the question I want to ask here is this really enough to achieve some kind of modular reasoning in quantum computing? So here I want to see the second observation. So let's say you now have a unitary circuit, and then you have proven this 2 specification, which says if the input is 0, 0 or 1, 1, then it behaves like identity. Now the question we want to ask is, what if we have another qubit which is entangled in this case? So here, entangled means like you cannot separate the state of x and y as a tensor product. But because, as I said, this is unitary, and it's linear, so you should be able to derive that it also behaves like identity in this case. However, frame rule doesn't allow it to like derive this immediately, because frame rule was only for disentangled resource. So that sounds like a limitation. We want to have something more. And the idea is, in our work, is just to add a linear algebraic structure for propositions. So what we introduced in our logic is that first we add a scalar multiplication for proposition and sum for propositions. And each of them correspond with usual vector calculus of them. And we also have a corresponding derivation rule for this. The first one says if you have a Hort triple, you can multiply some scalar to derive another one. Or the second one says if you have derived 2 Hort triples, you can just take the sum to derive another one. And this solves the problem. So let's see how it works. So this was an assumption. Now, with the frame rule, you can add another qubit. In this case, this is disentangled, so this is allowed. Now you can add a scalar to derive this. You can do the same game for the case of 1. And you can finally take the sum to derive the thing you want to have. So it works. Let me explain our idea in a little bit different perspective. So I want to make a claim here, which says this idea of adding scalar and sum bridges some kind of gap between intuitive proof and formal proofs in some senses. So the question I want to think here is that, so let's say we're given some kind of circuit, and we want to check this implements some kind of unitary U. And intuitively, what people usually do is that they say, it suffices to check the finite case of the basis case to prove this, and that is enough because of linearity. And in our logic, we can do the similar thing. So what we can do is that we can just check the Hort triple for these cases, and then finally, by using the scalar rule and sum rule, you can derive the thing we wanted to have. So because this reduces the problem into some basis, we wanted to call it basis locality. So that's the idea. Well, that's very simple, and probably too simple. And you might be wondering, why is that new, and isn't there any problem? Yes, there's actually a problem. So it's measurement. So measurement is problematic, because let's say now a program we're given is measurement, then because measurement doesn't do anything for the computational basis, you should be able to derive these two things, but by using scalar rule and sum rule, you'll be allowed to derive this, which says this measurement is equivalent to identity, which is completely wrong. So this is problematic. What's the problem? It's because measurement is not linear in this sense. Okay, we want to solve this problem. The idea to solve problem is that we want to be a little bit more precise in the pos condition. So let's think about this Horn triple, which says you want to measure something. And the pos condition I want to consider here is that something like this, which says after measurement, you create some kind of branching. And if you branch it to this side, you get ket 0. If you branch it to the other side, you get ket 1. And what is good about this idea is that if the input is linear combination, the output is going to be linear combination as well. And why is this true? It's because simply measurement is linear with respect to each branch. So let me formalize this idea in a logic. To do it, we're going to introduce another combinator, which we call mixing. And with this notation, so we use O+ notation with superscript that represents kind of ID for branching. And now with this combinator, we have this rule, which says if you measure ket 0, then you get ket 0 or some kind of state that never happens. And never happens is equivalent to say the probability is 0. If you measure ket 1, you get something similar, but on the other way around. And with these two rules, we can now safely use the sum rule and scalar rule to derive this one. And from here, I can just distribute this scalar like this. And then finally, we can take the sum. But here, when we take in the sum, we just add the left-hand side with left-hand side and right-hand side with right-hand side. And then now we can get this one, which is correct because this is not anymore saying this is identity, but rather saying like you can get two results. And corresponding to this mixing operator, we also have a rule for this, which allows you to combine two Horn triples by the mixings. And we want to call it outcome locality. So far, I have presented 3 localities, each corresponding to separating conjunction, sum, and mixing. And this is the core idea of our work. Okay, and corresponding to the new connectives we have introduced, we have in our paper we presented a lot of new rules that is useful for reasoning. I don't have time to explain everything, but if you're interested, I want you to take a look at our paper. But one thing I want to note here is that in some of the rules, if you want to prove left side from the right, it requires some kind of side condition. And I want to call this, I will call this side condition as frameability. And frameable propositions are some kind of nice propositions. And roughly speaking, these are the proposition that is constructed without using disjunction. And so, for example, every atomic formulas are frameable. And also, frameability goes under conjunction, separating conjunction, or sum or mixings. So in practice, a lot of propositions are actually frameable. OK, so in the rest of my talk, I want to talk about some kind of trade-off happening regarding the measurements. And also, I want to show how our logic actually scale in practice. One thing I haven't talked about is global phase. So what is global phase? Those are just a complex coefficient for a vector. And it is known that physically, these are not observable, meaning that this, for example, like ket1 or minus ket1 or I ket1 are observably equivalent. So we usually identify these three states. But however, in our logic, we cannot ignore these things. Why? It's because if we allow to ignore these things, that means we treat these propositions as an equivalence proposition. But because we have some rule, this allows you to identify these two things, which is completely different. So we're not allowed to do this. That means our logic is actually based on vectors rather than density matrices, because density matrices allows you to ignore the global phases. But however, like usual, like most of the existing quantum Horo logics are based on density matrices, because it's more natural to represent the measurement outcome with density matrices. And actually, there's kind of trade-off happening here. As I said, we wanted to have basis locality and sum. We had to use vectors. However, to represent the measurement outcome, in our logic, actually, in some cases, some kind of blow-up can happen for the outcome of the measurements. And more concretely, so let me introduce another notation of big O+, which just represents the O+. And after n measurements, you get n branching. That means you have 2 to the power n propositions combined with O+. And this is actually blowing up. And indeed, actually, blow up is sometimes unavoidable. So sometimes you might need to give up basis locality or scalability of size. That's actually true. However, what I want to say here is that in our paper, we presented a lot of case studies. And in those case studies, you can actually avoid this blow up, even though there are some measurements happening there, by doing some kind of smart way. So let me give an example for this. So the example I want to show here is this circuit, which is the error correction circuit for the bit flip code. I don't want to explain about the detail. You don't need to understand it. But one thing I want to mention here is that there are 2 measurements happening here. And so to verify some big circuit, or I mean, it doesn't need to be big, but to verify something, because of basis locality, you can reduce a problem into classical inputs. And now, because this circuit looks like classical circuit, if the input is also classical, you can easily derive this. So this is very easy. You don't need to understand a precondition or a postcondition, but yeah, this step is trivial. And one thing I want to focus here is that this part doesn't depend on the O+. And because of this, we can use the distributivity of O+ and separating conjunction. And by using it, we can put this last part to the front and leave the O+ to the rest. And what is important here is that because the rest part is not important, we can just forget it. Now, in this postcondition, we have existing quantifier for some favorable proposition, but there's no O+ appearing here. And we have proven this. And from this, we can just use scalar rule and sum rule to derive the thing we want to have. And one thing I want to note here is that I didn't mention, but frameability of P is actually used effectively here, so it's actually important. Yep, in our paper, we have presented a lot of other case studies, including algorithm which uses dirty qubits or quantum teleportation, and implementation of CNOT gate with 2-qubit measurements, which is the technique used in ladder surgery. And the next thing is something I just presented, and we also can also verify the correctness of short codes error correction. So this is a slide for related work. So the first line, Zhou et al. LIX 21 paper has introduced the quantum separation logic. And in the second line, POPL'22 paper added the classical variable treatment to it. And the next paper introduced kind of precise reasoning for probabilistic outcome to it. And our paper introduced basis locality to it. There's another quantum separation logic from Su et al., which is also a separation logic, but this treatment of separating conjunction is a bit different, so it's a bit hard to compare. Right, so this is the slide for conclusion. In our paper, we have introduced a new logic, which we call Rapunzel, and we have separating conjunction and sum and O+, and corresponding to these three things, we have a locality. And in our paper, we present a lot of practical case studies. And as a future work, we're considering extending to some relational logic, or we're also interested in automation. And also, I'm personally interested in adding concurrency or non-determinism to it. So, yep, this is the end of my talk. Thank you for listening. I want to have questions now.
Thank you. Questions?
Hi, thank you for the talk. So is there a way you can generalize this to generic superoperators? Like you gave a way you can do for measurement. So if you were considering the superoperators, which is like a general quantum channel, can you extend this logic to that?
I haven't considered about it. Maybe my answer is I don't know, but maybe interesting way to go on. Yeah, we can discuss later. Yeah, that sounds interesting. Thank you.
A clarification question. The plus for linear combination and the O plus for a mixture has very similar rules. Are there distinction like more logical in the sense that you want to the difficulty for measurement, or is the physics also different?
You mean, are you asking the difference between plus and O plus?
Yeah,
is
yeah.
that the thing?
Like, is there a difference in the physical world, or
Yeah,
did you
it
introduce the distinction for the logic to work?
Yeah, so plus is for superposition, which is, I don't know, it's a kind of, it's not a probabilistic difference, but O plus is the probabilistic mixture, which is some kind of classical superposition.
Okay, okay.
Yeah.
Sounds good.
Thank you.
I think there was another, yeah.
Okay, thank you for your clear talk. It's a great work. But to me, it seems it's more like symbolic execution on pure states. Do you think so?
Yeah, I mean, yes.
And you discovered a clever way to reason about it locally.
Yeah, I mean, yes, that's exactly how I see this, especially for this case study. So I didn't explain anything about something happened from here to here, but to derive this one from here, we just do the symbolic execution. And after doing it, in our logic, we can just generalize the input. So it's like a combination of symbolic execution and generalization to the every input. So I mean, I see the very relation between it.
So actually, my question is, in hologic, we talk about predicates because we don't talk about individual states. So what do you think is the predicate here? What is the difference between predicate and state? And what is your language for the predicate?
So I probably didn't understand what you mean by predicate. I don't understand the difference between the
in the
predicate
classical
and state.
case, we don't reason about the classical program state directly. We reason about logic formulas, right?
But I think, I don't know, yeah, we can discuss later, but yeah.
And also, it's about pure states, but in quantum algorithms, we always talk about probabilities.
Yep.
So are you considering extending this work to use density operator as the predicates or states?
So as I explained, our logic is based on vector states, but with this mixing of us, you can represent mixed state, not in the way people usually represent in the density matrices. If you use dense stream matrices, we lose basis locality, but that's the thing we wanted to have. But we still can represent, represent some kind of dense stream matrix in our logic as well. So we're not giving up some representation of probabilistic mixture of it. Does it make sense?
Yeah, thank you.
Yeah, thank you very much.
Questions?
Thank you for the talk. So I'm wondering about the scalability. I understand that all your case studies were done manually, right? Is it so?
Yeah, that's true.
And the examples that you show, it seems like very simple circuits, like maybe like 5-6 gates. So how about if you go for something bigger? Like, do you have some bounds on the size of the proof, for example?
The biggest example we have proven is this one, which uses this one as a building block. And, well, essentially, it's not big. It's not very big. I don't know how does it scale for the very huge one. That's kind of like a future work for us.
And the size of the proof, so is it somehow related to the gates, or how would you describe the size of the proof, for example?
Size of the proof. I don't know. I mean, the general idea is just like a symbolic execution here. So for each gate, we have one line for whole triple.
But I mean, like the size of the lines can grow, right? So
you can do one at a time.
So I'd like to add that, like, because we're using logic, we can do some kind of more like clever things. And as for the short code case study, as Kengo mentioned, like we use error-free code as a building block, and we can reuse the result like 3 times. So like in that sense, we don't need to like kind of actually simulate everything, but we can do like more clever replication of the existing results.
Maybe if there is one last short question, otherwise we can thank the speaker. And for those of you who are interested in quantum programming languages, there is another session on quantum programming languages on the very last day in the afternoon, so if you want to join.
gagner.
All right. Welcome to the session on decision procedures. We're going to start with our first speaker, Benjamin Prisboki. So please.
Work with Guillermo Toledo and Yanni Zohar. So this is characterizing sets of theories that can be disjointly combined. So let me explain something about what theory combination is. So theory combination is a subfield of SMT, satisfiability modular theories, which is the problem of determining whether a formula is satisfiable with respect to a given logical theory. So here we're generally going to only be considering quantifier-free formulas, as is typical. So there's plenty of decidable theories that are used throughout SMT solving. Some that you may have seen before are the theory of an uninterpreted function. This is where the signature has a single unary function symbol. We stipulate no axioms about this function. So this is a decidable theory, and an SMT solver could tell you that a formula like this is unsatisfiable. Another example would be something like linear integer arithmetic. This is where the interpretation is that the variables range over integers, and we have plus in multiplication by constants. This is another decidable theory that's used throughout SMT solving. But in practice, when we do applications to things like program verification and program analysis, SMT solvers often need to reason about multiple theories at the same time. So what if we wanted to decide the satisfiability of a statement like this one? So this is mixing the vocabulary from both the theories of linear integer arithmetic and that of the theory of an uninterpreted function symbol. So you can see we have less than or equal to operator and minus coming from integer arithmetic, and we also have an uninterpreted function in there. And so the question is, given decision procedures for these two component theories, how can we modularly combine them to decide the satisfiability of a sentence like this one? And that's the general question of a theory combination. So once again, given decision procedures for theories T1 and T2, when can we construct a decision procedure for their combined theory? And by the combined theory, I literally just mean the theory obtained by taking the union of the two axioms. And I'm going to assume throughout this talk that these are theories over disjoint signatures, so they don't share any function symbols or relation symbols. Okay, so let me start by explaining some background on theory combination before delving more specifically into our contributions here. So Nelson and Oppen, back in 1979, they initiated the study of theory combination by proving a criterion that suffices for two theories to be combinable. So it involves this notion of stable infiniteness. So we say that a theory is stably infinite if for every T satisfiable quantifier-free formula, it's satisfied by some infinite T interpretation. And what Nelson and Oppen showed is that if we have two decidable theories over disjoint signatures that are both stably infinite, then their combination is decidable. And this is a completely constructive argument. So there's a constructive way to construct a decision procedure for the combined theory from the component theories. Okay, so that was the state of the art for about 20 years. Although in practice, the requirement that both theories be stably infinite has proved to be a hindrance for some applications. So naturally, researchers turn to other questions, other possibilities for how to combine two theories. And motivated by this, Tinelli and Zarba proposed a different combination method using a property that they call shininess. So they say that if a theory is shiny, then it can actually be combined with any other theory, any other decidable theory, with no requirements imposed on the other theory, besides that it be decidable. And I'm not going to define exactly what shininess is, but the key thing to know is that it's some property that's stronger than stable infiniteness. So this theorem is logically incomparable to the Nelson-Oppen theorem, but what it is it's formalizing a different trade-off between the theories T1 and T2. So we impose a stronger condition on T1, and the advantage is that we no longer have to impose any condition on T2. Okay, so in general, more abstractly, we can say that a combination theorem is of the form, if T1 has property P1 and T2 has property P2, then the combination of T1 and T2 are decidable. And once again, I'll assume throughout that the component theories are decidable and over disjoint signatures. Okay, so there's several of these combination methods in the literature. I already talked about Nelson-Oppen and shiny. There's also one called polite and gentle combination. And you can see from this table that shiny combination and polite combination seem very similar in that they only impose a requirement on one of the two component theories. But actually, their similarity lies deeper than that, because there's a surprising result of Casal and Hasga that a decidable theory is shiny if and only if it's strongly polite. So in some theoretical sense, you can think of these combination methods as being the same. They apply to exactly the same classes of theories, although there are still important implementation differences between these two. So for example, polite combination is used in the CVC, in the SMT solver CVC5, so it's a very practical choice for combining theories. Okay, so this is several sufficient conditions for theories to be combinable, but the central question in our paper is looking at the opposite. What can we say about necessary conditions for pairs of theories to be combinable? And in particular, one thing we want to know is, can any of these combination methods be improved to apply to a larger class of theories? If they could, then this would open up the door to combining more pairs of theories within SMT solvers. So this is something that people have been interested in for a while. So back in 1996, Tonelli and Harandi conjectured that there might exist weaker requirements on the component theories, which are sufficient for the Nelson-Oppen procedure's correctness. So they're conjecturing that the Nelson-Oppen procedure can be improved. We can impose some requirement weaker than stable infiniteness. And then again, a similar sentiment was expressed in 2018. So Casal and Hasga expressed a desire to find a class of theories strictly containing the shiny or strongly polite theories, for which there exists an indiscriminate theory combination method, in the sense that they can be combined with an arbitrary decidable theory. And so the central contribution of our paper is to show that the following negative result, that none of the aforementioned combination methods can be further improved to apply to larger classes of theories. So all those 4 methods I mentioned are provably optimal. And when I say cannot be improved, let me say more precisely what I mean by that. So for this Nelson-Oppen method, that means that stably infinite theories are the largest class of decidable theories that can be combined with all stably infinite theories. Similarly, shiny theories are the largest set of decidable theories that can be combined with all decidable theories. And finally, gentle theories are the largest set of decidable theories that can be combined with all theories with computable finite spectra, and vice versa. So I'm not expecting you to know what all these properties are, but this is basically saying that these methods are optimal in that sense. Okay, but our results are not all negative, so we also have some positive results. So en route to proving these results, we also introduced a framework for studying and classifying theory combination properties. And specifically, what I'm going to explain in a minute is that we show that there's a lattice of theory combination properties that's induced by this Galois connection that pairs up properties that are amenable to combination. So this is just a glimpse of this lattice that I'm going to describe later, and I'll show you what these, how to interpret it. And so this facilitates the discovery of new combination methods. And actually, in our paper, we prove several new combination methods. And those combination methods are all sharp in the previously mentioned sense. So they also cannot be improved. But again, they formalize a different trade-off between the properties that we impose on T1 and T2. Okay, so let me explain what the Galois connection is. So we'll let this fractor T be the set of all decidable theories. And then X will be some subset of decidable theories. So some set of decidable theories. And we'll let G of X be the set of decidable theories that can be combined with every theory from X. So there's 2 properties I want to observe about this. The first is saying that this G function is antitone. And the second is saying this property that if X is a subset of G of Y, then Y is a subset of G of X. So these properties, once you unfold the definitions, these properties actually are saying something very simple. So the first one is saying that to say that G of X is a subset of G of Y is to say that if some theory can be combined with every theory from Y, then it can be combined with every theory from X. And that's true based on our assumption that X is a subset of Y. So that's basically just trivial once we unfold the definition. The second condition is saying, the way to read this is that if every theory from X can be combined with every theory from Y, then every theory from Y can be combined with every theory from X. And again, that's just a tautology. So the reason I'm mentioning these 2 conditions, though, is that these are exactly the conditions that characterize what's called an antitone Galois connection. And this is a very nice algebraic structure, and I'll show some of the nice consequences of this in a minute. Okay, so we have this Galois connection, and now let me show this how this can be used to reframe some of our results within the language of this Galois connection. So I'll let T shiny, for example, be the set of shiny theories. And what I said earlier is that Tonelli and Zarba showed that shiny theories are combinable with every decidable theory. So we can write that as saying that T shiny is a subset of G of T, because recall that T is the set of all decidable theories. And we're saying the converse. So we're saying that shiny theories are the only theories that can be combined with every decidable theory. So equivalently, G of T is a subset of T shiny, because G of T is the theories that can be combined with every decidable theory. So the thing I want to observe here is that if X is a subset of G of Y, this means that there's a combination theorem for the pairs of theories X and Y, in the sense that there's a general method that will combine any pair of theories taken from X and Y. And if, moreover, we have an equality, then this combination method is sharp, meaning that it cannot be improved at all. It's impossible to enlarge either x or y, while preserving the property that any pair of theories from these two classes can be combined. And then observe as a consequence of this definition that a subset of theories participates in a sharp combination theorem if and only if x is equal to g of x, in which case we say that x is closed, because this g operator iterated twice is actually a closure operator. That's a consequence of the Galois connection. So we really want to focus on these closed classes of theories as theories that naturally form part of some theory combination method. And another consequence of the Galois connection is that the closed classes of theories form a complete lattice. So this means that they're closed under arbitrary meets and joins. So this means that there's a complete lattice of theory combination properties, each of which, according to the Galois connection, is paired with some other class with which it can be disjointly combined. Okay, so far I've just been stating things in this abstract framework, stating definitions. But now let's actually go into the details and say how would we prove something like this. So how would we prove that g of t is a subset of t shiny? So I'm going to explain at a high level roughly how we do this. So we'll let t be an element of g of t, and recall that what that means is that t can be combined with every other decidable theory t prime. And now we want to show that t is shiny. Okay, so the idea is that we're going to cook up some decidable theory t prime, such that if t can be combined with t prime, then this forces t to satisfy some desired property. I'll give you an example of this on the next slide. And we call t prime a test theory because it's basically testing whether t has some property. And if we probe t with enough test theories, this allows us to deduce enough properties about it to conclude that it's shiny. So let me show how this works for one property. So the shininess is I'm not going to give the whole definition, but one aspect of shininess is a shiny theory has the finite model property. And the finite model property means that for any quantifier arbitrary formula, if it's satisfiable, then it's satisfied by some finite model. So it has a finite t interpretation. Okay, so here's how we're going to make our test theory. So let f be the number of steps it takes for the nth Turing machine to halt, according to some enumeration of Turing machines, or we'll let it be infinity if that Turing machine diverges. The key fact about f to recall here is that it's undecidable whether f of n is equal to infinity or not. That's the famous halting problem. Okay, so now we're going to define this somewhat strange-looking theory t less than, which has infinitely many nullary predicates, Pn, for each natural number n. And it's going to be axiomatized by Pn implies that there are at most f of n elements, assuming f of n is finite. And note that saying that there are at most f of n elements is something that we can say in first-order logic. So in first-order logic, we can express the statement that there's at most some finite number of elements. Okay, so perhaps surprisingly, we prove that t less than is decidable, even though it's defined in terms of this weird non-computable function. It's still decidable. And this is going to be exactly the test theory that we need to show that t has the finite model property. Okay, so suppose for the sake of contradiction that t does not satisfy the finite model property. So then there's some formula phi that only has an infinite t model. And then phi and p of n is satisfiable in the combined theory if and only if f of n is equal to infinity. And the reason for that is that phi only has an infinite model, and p of n is saying that there's at most f of n elements. So if that's the case, then the only way that those two things can be compatible is if f of n is equal to infinity. Okay, so in other words, we can test whether f of n is equal to infinity by asking whether phi and p of n is satisfiable in the combined theory. And by assumption, the combined theory is decidable. So this gives us a decision procedure for determining whether f of n is equal to infinity. That's a contradiction. That contradicts the undecidability of the halting problem. Okay, so that's one aspect of the proof. And basically, in the paper, we're doing a bunch of these sorts of things where we have to come up with some test theory to determine whether a theory has a desired property. Yeah, so it's a bunch of theories that are defined in terms of weird non-computable functions, but nevertheless turn out to be decidable for non-trivial reasons. Okay, so that was something about how we actually proved these sharpness results. An interesting, surprising corollary pops out of our results, which is as follows. So there's a decidable theory t prime, such that for every other decidable theory t, if those two theories can be combined, then t can actually be combined with every decidable theory. So there's actually like a theory that's maximally difficult from the standpoint of theory combination. And the reason is actually a simple corollary of our proof, because in our proof, we show that there is a single test theory that forces combinable theories to be shiny. And once you're shiny, you can be combined with any decidable theory. So that was something that we would not have at all expected this to be true beforehand, but then we looked at our proof and we sort of observed that this is like a nice corollary. And you can think of this as being analogous to complete problems in complexity theory, like a maximally difficult problem. So this is sort of a new phenomenon in theory combination that seems to have been unnoticed so far. And we similarly have these sort of maximally difficult theories for all the other for most of the other theory combination properties in our paper. So for example, there's a maximally difficult stably infinite theory. This is a stably infinite theory such that if a theory can be combined with that, then it can be combined with all stably infinite theories. Okay, so that was something about tightness. Now I want to say how we actually use our framework to discover new combination methods. And we have a couple ways to do this. So one is what we call taking the closure. So what I mean by this is for some existing combination theorems that are in the literature, it actually turns out that they're not sharp. And we tried to prove that they're sharp, and we got stuck, and we realized, okay, we can actually improve this theory combination method to a more general version. And we call this taking the closure of a combination method, because we're upgrading a combination theorem involving a class of theories X to one involving its closure, G of G of X. And having a nice stock of test theories is helpful for not only discovering that a set of theories is not closed, but determining what its closure is. Because we can use its various test theories and test whether it's combinable with those. And that tells us something about the properties it satisfies. So there were a couple of combination methods in the literature that we were able to improve to get a sharp one. The other ways is by more so exploiting the algebraic properties given to us by the Galois connection. So recall that the closed sets of theories form a complete lattice, and their meet is given by taking the intersection, and their join is given by taking the union and then closing that set of theories. So this means that we can discover new combination methods just by taking old methods and taking meets and joins of these theory combination classes. And taking the meet is just trivial, it's just the intersection. Taking the join is a little more involved because you not only have to take the union but also close it. But the test theories can be helpful for doing this. And once you have a theory combination method derived by this method, it's sharp by construction. So one method that I want to showcase, because it's just independently interesting, and you can read the paper to see more on how we actually derive this, is what we call the computable spectra method. So say that a theory has computable spectra. If there's an algorithm that, given a quantifier-free formula phi and a cardinality k, decides whether phi has a model of size k. So I think that's a fairly natural condition. And the reason we consider that is because it's actually the meet of two other conditions that have already been studied in the literature. One called computable finite spectra, which is a weaker notion, and then one called infinitely decidable. And so we know that there's a combination method involving this class. And in fact, it turns out to just be a totally symmetric method. So what we can say is that if we have decidable theories over disjoint signatures that both have computable spectra, then their combination is decidable. And this is, of course, sharp. So I like this because it's sort of the first, as far as I know, it's the first combination method since the Nelson-Oppen method that's symmetric in the sense that it imposes the same requirement on both component theories. Though this requirement is logically incomparable to the Nelson-Oppen, so it's neither weaker nor stronger than stable infiniteness. Okay, so here's part of the lattice of theory combination properties that we have. So the way to read this is that these are each of these elements of the lattice is a class of theories, and the Galois connection pairs it with its reflection across the horizontal line. And these are ordered by inclusion. So at the very top, we see T, that's the set of all decidable theories, and if we reflect it, we get T shiny. So that means that there's a sharp combination method between all decidable theories and the shiny theories. On the far right, we can see that we have TSI, those are the stably infinite theories, and those are combinable with themselves. Here in the middle, we have TCS. This is the theories with computable spectra. Those are again combinable with themselves, and you can see that we have several other combination methods, some of which existed before us and some of which are new due to us. And I should say that there's really not many properties about this lattice that we know. All we know is that it's we know that it's a complete lattice. We don't really know much else besides that. So in particular, we don't even know whether it's a distributive lattice. That would be nice to know given the demonstrated utility of computing meets and joins. Although we don't really expect any reason, there to be any reason for it to be distributive, but we haven't found a counterexample. The other thing is that we know that the lattice is infinite. So we actually do describe an infinite family of theory combination methods. In fact, an uncountably infinite family. So the space of theory combination methods is quite rich. Okay, so to conclude, ever since Nelson and Oppin's seminal paper in 1979, one of the central theoretical questions in theory combination has been when two sets of theories can be disjointly combined by a modular combination procedure. And we make progress on this problem by exactly characterizing the sets of decidable theories that can be combined with those satisfying well-known theory combination properties, like stable infiniteness, shininess, strong politeness, gentleness, and so on. And so this answers in the negative several long-standing open problems about the possibility of improving these methods. And not only that, our framework also, as we saw, facilitates the discovery of new combination methods. And if you want to see even more than the one I presented here, there's several more examples in the paper. Okay, so this resolves several problems, but it also opens up several new avenues for future work. One is that we want to generalize these results to many-sorted logic. So in this paper, we only deal with single-sorted logic for simplicity, but SMT solvers often want to work with many-sorted logic as the standard. And that introduces some technical complications. They should be surmountable, but it's a generalization that we want to pursue. Another is to better understand the lattice of theory combination properties. So for example, we would like to know whether this lattice is distributive, whether it satisfies any other nice algebraic properties. And then finally, another direction that's a little more speculative is non-disjoint theory combination. So this is theory combination when the signatures of the theories share predicate or function symbols. And this is a lot less well explored than the disjoint case. There's only a few papers on it. But perhaps some of the techniques that we developed for our paper could be useful there. So thank you. That's all I got.
Okay, thank you. Our questions? There in the back.
Thanks, very nice results. Do you get also something about the complexity of the theory combination, or do you think these lattice theoretic results could apply to say something new?
Yeah, so this is I thought about mentioning this on the slide as a future direction. We mentioned this in the paper as something that could be a good future direction to explore, but the answer is actually, so yeah, no, we don't really get any nice complexity results characterizing. So in some cases, the combination procedure we have isn't even primitive recursive in general. So it would be nice to also look at maybe a more restricted form of combination where we insist not only that the combination be decidable, but that it be decidable with a computational complexity that's not much greater than that of the component theories. So I think that's a really interesting direction.
Thanks for the nice talk. The results are very good. So is there an assumption that that we're only looking at quantifier-free formulae?
Yeah, only quantifier-free formulas.
So do you think the results would at least slightly extend to the case when we have quantifiers?
No, I don't think any of them will, because yeah. So this is also something that I think is an interesting future direction, but I don't know much about it. So there's several counterexamples of theories whose combination is undecidable. So for example, like Presburg arithmetic, if you add a single unary predicate symbol, it becomes undecidable with quantifiers, even though both of these theories are very simple and in fact stably infinite. So I don't really know a nice characterization of when a combination of a full first order theory is decidable.
And likewise, is there is there an extension that would also apply for higher order logics, like second order logic, for example?
I imagine that there would be similar. Yeah, it's not something I've thought about, but I imagine that these results themselves would not generalize.
Thank you.
So thank you for the talk. Do you have any results about the combination of more than two theories?
Yes, so some of these methods can be extended to more than two theories. So, for example, Nelson-Oppin says that if you combine two stably infinite theories, it's decidable. But also, if you combine two stably infinite theories, the result is stably infinite. So then by induction, if you have n stably infinite theories, you can combine them all. With the asymmetric methods, things like shininess, the generalization is that you need n minus one of your theories to be shiny, and the other can satisfy any property. And that's because the combination of two shiny theories is shiny. But then once you combine it with a non-shiny theory, the combination is no longer shiny. So then you can only do that once. Yeah.
So maybe one last question before, but in the meantime, the second speaker can maybe set up already.
Hi, I'm Joseph from Purdue University. So it's natural to extend like the decision problems to like a unification problem, like what the mod theorem improver does. If you consider like complete sets of unifiers or most general unifiers, does your work, do you know if it extends to those kinds of problems at all?
Like you're asking, given a method for computing unifiers in two theories, can you compute a unifier in the combined theory?
Yeah, in the disjoint, yeah, combined theory.
Yeah, that's something I've thought about, but
Okay.
it sounds like an interesting problem.
Thank you.
Okay. Yeah. Thanks again. And
Hello? All right.
please, go ahead.
Cool. Hi, everyone. My name is Nikhil Pimplakare. I'm a final year PhD student at Princeton, and I'm going to be presenting on some joint work with Zachary Kincaid, my advisor, and Thomas Reps on context-free reachability for almost commuting transition systems. So the motivation of this work is to design new techniques for interprocedural program analysis. So program analysis is broadly about automatically computing properties of programs from their source code. And interprocedural means that the programs that we consider have function calls. So in this example, in the program on the left, it's got a recursive function call in its body. In this work, we consider a formalization of interprocedural programs which separates data and control. The way in which a program modifies data is modeled as a labeled transition system, and the way in which, and the control structure of the program is modeled as a context-free language. So on the right, we have the formalization of the program on the left. The control structure of the program is modeled by the context-free language generated by the grammar G. G generates a language by repeatedly replacing the start non-terminal S according to the production rules until you have a string of all terminals. So in the context of the program, the S non-terminal represents a run through the foo program. The A and B terminals correspond to the A and B operations in the program. And the production rules kind of identify the possible paths through the program. So either we just apply the A operation, or we do A operation, recursive call, then B operation. And the data manipulating semantics of this program are modeled as a labeled transition system, which is written here as two transition formulas. So the unprimed variables represent the pre-state, and the primed variables represent the post-state. So the transition corresponding to A says that X gets incremented by 1 and Y gets preserved, and the transition corresponding to B says that X gets preserved and Y gets incremented by 1. And these transition formulas model the state effect of the corresponding operations on the program side. And so we formalize the procedure on the left as the behavior of this labeled transition system along a context-free language of program paths. Our goal is to compute the reachability relation of this system, so the set of input-output state pairs that are connected by a sequence of transitions along a path in the context-free language. So the kind of abstract picture is here. We have a context-free language representing the program structure, and we have a labeled transition system representing the program semantics, and we want to compute the context-free reachability relation of the transition system. So this is the set of state pairs that are connected via the transitions along something in your language. I'll mention that sort of the key weakness of this formalization is that since it doesn't have access to unbounded memory, it can't model local variables, but it does provide a sort of mathematically clean way to answer research questions. And so in this work, we aim to answer the question, for what transition systems can we compute this context-free reachability relation? So this slide kind of recaps everything. So we understand interprocedural program analysis as computing this context-free reachability relation, and transition systems map each character in a finite alphabet of edges in your graph to some relation between input-output state pairs. And we want to compute this object, which is the set of state pairs that are connected by a sequence along the context-free language. So in order to answer this question, what transition systems are interprocedurally analyzable, we're first going to have to consider what theoretical tools we have to reason about context-free languages. So an important classical result is that we can compute the Peric image of context-free languages. So the Peric image of a word is a character count abstraction of it. So the Peric image of this word identifies that there's 2 A's, 3 B's, and 1 C, but loses all information about the relative order in which these characters appear. And the Peric image of a language is the set of Peric images of the words within it. And so Peric's theorem, which is a classical result from 1966, says that we can, it says that, and along with this other result from Verma et al. In 2005, say that we can compute a logical formula whose models define the Peric image of a context-free language. And so what that looks like is when we have this is the grammar from the beginning, and this is the language that the grammar generates. So the Peric image of this context-free language identifies that you're always going to have one more A character than B character, because every time you use the second production rule, you get one of each, and then your derivation is going to end when you use the first production rule, and that's going to give you 1 extra A. And so there is an efficient procedure for computing a logical formula like this one, which says that we're going to have a non-negative number of A's and B's, and we're going to have one more A than B. And we can use this formula in order to automatically compute the context-free reachability relation of programs in which all of the operations commute. So this is the program from the very beginning. This is the grammar that generates the paths through it, and the under-bracketed part of the formula is the Peric image formula from the previous slide. And since all of the operations in this program commute, we know that when we apply NA A operations and NB B operations in any order, we're going to have that X gets incremented by NA and Y gets incremented by NB. And so we're able to use the Peric image in order to automatically compute this formula that's defining the context-free reachability relation of this program. This is the kind of image. So in order to get the reachability relation of this commutative transition system along paths through the context-free language, we can sort of factor through its Peric image and use the universality of that object in order to compute the object that we want. I'll take a slide here to talk about what's happening sort of mathematically. So every transition system corresponds to a monoid. A monoid consists of a domain M, a composition operator that says how you take 2 things in your domain and combine them to get another thing in your domain, and an identity element. And transition systems can be sort of modeled inside of monoids in which the monoid operator is relational composition, and the domain is the closure of the base transition relations under relational composition. And so the Peric image is the universal commutative abstraction of languages. And so a key corollary of Peric's theorem is that we can compute a logical formula representing the image of a context-free language under a homomorphism into a commutative monoid. And in the context of this transition system monoid that I defined at the top, what this means is that we can sort of use this recipe in order to compute the context-free reachability relation of commutative transition systems. All right, so that's all pretty cool, but a lot of programs are not commutative. So this program is not commutative. The x equals negative x plus 1 is not going to commute with the other operations. And so it's unclear that we can use the Peric image in order to automatically compute the context-free reachability relation of this program. But we can via the contributions of this paper. So this paper extends the scope of context-free reachability to a rich new class of transition systems, which are these almost commuting transition systems. And the way in which we compute the context-free reachability relation of these systems is that we compute an unfolded, bigger context-free language. We take the Peric image of that language, and we use that object in order to compute the thing that we want. So what is a almost commuting transition system? I'll start by example. So we identify a couple of different transitions which induce these almost commuting transition systems. And zooming in on the top one, kind of the key property of these transitions is that they can factor into a transition from a finite set acted upon by a purely commutative component. And so this kind of decomposition is kind of the key thing that makes this operation almost commuting. These other classes, the decomposition is a little bit more complicated, but they also have decompositions in which they can all be turned into a transition from a finite set acted upon by a purely commutative component. So these are some examples of almost commuting transition systems. The way in which we formally define an almost commuting transition system is if the monoid that represents the transition system is an almost commuting monoid. So remember, each transition system corresponds to a monoid in which the composition operator is relational composition and the domain is the closure of the base transition relations. So a monoid is almost commuting if each element factors into one of finitely many monoid elements acted upon by a element of a commutative integer monoid. And additionally, the monoid operator meets this second kind of simple algebraic condition that's a little bit too technically subtle to discuss in this talk. And the key result of this paper is that we can compute a logical formula representing the image of a context-free language under a homomorphism into an almost commuting monoid. And like with the Peric image, we're going to use this to compute the context-free reachability relation of almost commuting transition systems. I guess to repeat, the sort of recipe that we use in order to compute this reachability relation is that we unfold our context-free language into a bigger context-free language. We take its Peric image, and then we use that in order to compute what we want. And I'm going to show you how this recipe works in the context of a program. So on the left is the non-commutative program that we saw before. That's actually an almost commuting transition system. And on the right is the result of doing this unfolding. So in the following slides, I'm going to try and convince you of two things. First of all, that this unfolding is equivalence preserving. So the input-output behavior of foo is equivalent to the input-output behavior of foo shell. And I'll also try to convince you that we can compute the input-output behavior of foo shell from its Peric image. So let's start by trying to prove equivalence. We want to prove that the orange program is equivalent to the pink program. And I'm going to do this, try to be convincing just by showing a single example trace. So here's a trace through the orange program where we take the recursive case 5 times, and then we hit the base case. And there should be 4 more C operations, but I haven't diagrammed here because I'm only looking at what happens to the X variable. All right, so what I'm going to do is I'm going to multiply through the negations in each of these terms. Now, this trace through the orange program corresponds to this trace through the pink program. So foo even and foo odd describe the number of times that the x variable will be negated in the remainder of the trace. So the first operation in foo shell guesses whether there will be an even or odd number of negations throughout the trace. In this case, there is an odd number of negations, and so we're going to pick the one operation. And then the increments within foo even and foo odd are modified based on the context that they have about the remainder of the run. So for example, the B operation is incrementing x by 1, but the B0 operation is subtracting 1 because it has the additional context that the following foo odd call is going to perform an odd number of negations to the x variable, and we're going to end up with a decrement. So the trace through the pink program records increments in the final context in which they'll appear. So this means that at intermediate points throughout the trace, the pink program does not have the same x value as the orange program. But this is because the increments are happening in the context in which they'll appear at the very end. And so by the time we reach the end of the trace, both traces have computed the same x value. So in this way, every trace through the orange program corresponds to exactly one trace through the pink program. And foo is equivalent to foo shell. All right, and we can compute the input-output behavior of foo shell from its Peric image. So this is a set representation of the Peric image with this sort of operation order. So the top is the foo even case, in which we basically have an equal number of alternations between foo even and foo odd, ending in an A0 operation. And the second set is the odd case, in which we have one extra B1 operation, and then we have the even case, and then we have one extra C1 operation. And we can use this Peric image in order to compute this sort of non-trivial procedure summary of foo shell, in which the first set corresponds to this first disjunct, and the second set corresponds to the second disjunct. The first disjunct says that x is not going to get negated, y is going to increase by 2k because both C0 and C1 are incrementing y, and then the B0s and B1s will cancel out. And similarly, we end up with the second disjunct from the second set. And so we were able to automatically come up with the context-free reachability relation of this program from its Peric image after we had unfolded it. So I'll hint that this unfolding is guided by the underlying structure of the almost commuting transition system. So the finite set of transitions that are forming the decomposition, that's going to determine the size of the blow-up to get the other language. So what transition systems are interprocedurally analyzable? Almost commuting transition systems. This paper identified a rich new class of transition systems for which we can compute the context-free reachability relation. We identified several examples of transitions generating almost commuting transition systems, and we computed the context-free reachability relation of these systems by unfolding our context-free language and using its Peric image. So this work can be viewed as a backend for an abstract interpretation-based program analysis. So a client would have to pick a suitable family of almost commuting transition systems and develop an abstraction procedure. And then they could use our work as a sort of backend in order to automatically compute the reachability of that abstraction and end up with an overapproximation of the original program. And this work can also be viewed as an expansion of the applicability of Peric's theorem to almost commuting monoids. Thank you for listening.
right, thanks. Are there any questions? Let's start here.
Several slides ago, you showed a rewriting of your original program into the almost commutative transition system. I wonder, like, if Daniel's choice is instead of non-deterministic, it's probabilistic. Is this kind of rewriting still possible? Like, would they still be equivalent? Or does this question even make sense?
I think that, so it really depends on, so you can replace this predicate, the even x, with different predicates, potentially probabilistic ones, but I would say it's like highly dependent on which particular predicate you put in to make sure that you still end up with the finite set.
Sounds good, thank you.
On one of your earlier slides, you gave the kind of rules for your almost commuting transition systems, which essentially said your variables were over Z. So I wondered if you had like a multilinear version. So rather than just like these linear transitions you gave, could you use matrices, which don't often commute, but you might have similar rules? Or is it something to do? Yeah, so you were on the slide just then.
Was it this one?
No, there's like the one with more text.
Oh.
There we go.
Sorry, this one.
Yes.
Okay, yeah.
So you have a commutative integer monoid. So I wonder whether you've got this kind of system over a Z. Could it be over Z to the D, say, or whether there's any...
It can be over Z to the D. I guess I wrote it as an integer monoid here for simplicity's sake, but really the property that we care about is that it's finitely generated.
Wonderful.
Thanks.
The examples that you gave us on the slides were, of course, very small, like academic examples, but I'm sure you have some kind of more practical things in mind when you develop this theory, probably some examples of things that you would like to analyze, right?
Yeah, so this sort of actually, this top class of transitions, I guess one of my prior works at POPL'26 in 2024 designs kind of a practical abstract interpretation-based technique, which uses this in order to compute resource costs and to model different aspects of programs. So there are practical use cases for this.
Okay, thanks. Maybe one last question while the next speaker sets up. Okay. So maybe I could ask a question while the last speaker sets up. So you had these, you use context-free languages to model these traces, but of course there you're over-approximating. Mm-hmm. Do you think there's a generalization to something context-sensitive where you could do the analysis by looking, for example, at the condition statement?
I think it's possible that you could apply additional formulas. You could refine the Perick image formula in order to be more context sensitive. But off the top of my head, I don't know of work that computes such formulas. Yeah.
Okay, thanks. Yeah, thanks again for the talk. And now we have George as our last speaker for the session.
Hi, thank you for coming today. And let me just say that this is joint work with my colleagues, Rita Etamasson, Massa Shamhamadi, Anton Varonka, and James Worrell, sometimes known in the community as Ben Worrell. I'm going to explain what a determination problem is and what orbit closures are, and we'll try and leave the kind of difficult mathematics until the very end. In particular, Nikhil just gave a great reachability question in his talk, where he was talking about transitions through a given program. In our setting, that reachability question could be thought of in terms of a finitely generated group of matrices, and then I give you one vector as an input, and I give you one vector as an output, u and v, and I ask whether there's a group element from your finitely generated subgroup such that you can make that transition from one point to the next. So this orbit problem has been long studied. In particular, if you take a general matrix group, the problem is undecidable. But it's decidable in the commutative case. And in fact, from about the early 70s, if you worked with just a cyclic group, so a single generator, you could actually decide this reachability question in polynomial time. So with this idea that actually the problem of reachability is generally undecidable for matrix groups, why not make your life simpler? And by simpler, I mean we're not going to consider orbit questions properly, but orbit closures. So I understand that orbit closures might not be the kind of the most well-known thing today, but they've recently appeared in lots of different papers in the context of, say, the threshold problem, or resolving the threshold problem for quantum automata, perhaps even the equivalence problem of deterministic top-down tree-to-string transducers. And also when you're trying to think about invariance or algebraic invariance of certain looping programs, they all appear in these different contexts. So just before we move on, when I say that it doesn't work in like a commutative setting, what I've written on the right-hand side is the kind of looping program I'm interested in. So these stars, they're going to be non-determinate. You can evaluate these asterisk symbols as either true or false non-deterministically, and within each iteration of the loop, your branches is either going to pick a linear update, so you're taking a vector, you're updating it by either matrix 1, matrix multiplication against a vector, or you're updating it with matrix 2. And then it doesn't matter, we don't really care about the termination of the loop in particular, we're just interested in how it's running. We're particularly going to focus on algebraic invariance in this talk today. So what do I mean by an invariant? This is just going to over-approximate the set of reachable points of your loop program. So I've got some, there are 3 of the diagrams on this page that have the same system of dots, the top 2 and the third one, or the first one on the second row. And of course, I've drawn a pink set over these reachable states, and depending on what type of over-approximation you allow, you can get different shapes of sets. The next 2, the bottom 2, are the ones that I'm kind of more interested in from our point of view. So one of these just draws like a y equals x, or plus some kind of constant line through some points. So this is a linear over-approximation. But if I wanted to draw linear sets over the second, or the third bottom picture, I'd have to use lots of different lines. But we have a nicer line, this pink looping line, y squared is equal to x squared plus x cubed, which does it all in one simple. So somehow we might consider this a better approximation. So just to kind of point out here, I'm going to be interested in algebraic sets. They're just going to be the common points or zero loci of families of polynomials. So they're just going to be polynomial solutions, but in maybe several variables. Here, on this slide, I've obviously done it in 2 variables, but you could do it in as many variables as you like. Now, let's try and go with an example to begin with. So I'm going to give you my favorite algebraic set. I say favorite because I use it on all of my talks. And I'm going to say to you, well, I want you to jump using a dynamical system only on the pink line here. So you could think of yourself as like a rabbit or a frog jumping in 2 dimensions here. that's actually what I'm really asking you to do, is to kind of take an incomplete program, and these jumps I'm going to ask you to be linear. So the elements you have to fill in here are thus a 2x2 matrix and an initial starting point, which will be alpha. And then, so long as you stay inside the pink set, you've got this kind of what we call an orbit, alpha, m squared alpha going through. So this isn't quite the whole problem, though. Because if I left the problem statement as it is, you're allowed to choose the trivial loop. So this is kind of a cheating method. Don't do this one. So with one single point, you would obviously solve this problem, which is uninteresting. So let's not do this. I should say that's why the asterisks appeared. We have this kind of maximal notion here. Maximal in the sense that for the purpose of liveness properties, I want to explore the set of, or the kind of specification as best that I can. So let's try and ignore this kind of rubbish solution here. And instead, why don't I give you my favorite solution then? So if I take this particular matrix, 1, 1, 1, 1, 1, 0, and I give you the starting point 1, 0, if you feed your alpha into the set Z, I can evaluate it as 0 squared plus 0 minus 1, but obviously that's a plus 1, minus 1 is equal to 0. Okay, so we've started on the pink line. Great. And then when I do a jump, I might switch to a different kind of fiber or a different line in my polynomial set, but that's okay. I keep flipping back and forth. And what you should notice about this particular kind of variables that are happening here, your favorite linear recurrence sequence might be occurring. That's 0, 1, 1, 2, 3, 5, and going forth. So what I've actually done is I have generated the Fibonacci numbers and the Fibonacci numbers plus 1, so consecutive Fibonacci numbers in x and y. So actually, some of you who might have a mathematical background might recognize that actually the polynomial, this polynomial that appears inside the set Z is actually Cassini's identity, which relates two consecutive Fibonacci terms. So all I want to take away from this is that somehow the solution I've given here is the best solution, even though I have left out all like there are two curves I've not even touched in this set. I've actually covered in a polynomial way the entire set as best as I possibly can. Okay, so moving on, like what if I took this from a mathematical setting, but I said, let's do it in loop synthesis. So loop synthesis being a type of program synthesis, but I'm doing a very specialized case. So we start with our same input, and then I rewrite the problem slightly. I want to now come up with a loop of a specified form. So I just have an input, and then I have a linear update. And I want tightest or maximal, one of these types of adjectives. And why do I call it tightest or maximal? It's because somehow the best choice, or the maximal choice, will be the closure in the Zariski topology. You don't need to know what the Zariski topology is for the purpose of this talk, but it's saying that in a polynomial sense, this was the best choice that we gave. If you're more into your Hoare logic or Hoare triples, then of course I could ask you for a satisfying pair, i.e. some matrix and some vector, such that the two Hoare triples at the bottom of the screen are satisfied, and my maximal condition just says, oh, well, I want the best possible polynomial approximation, what we're going to call this orbit closure. So I should say that actually, if I did give you this example and you wanted to compute the best alpha and m, which we did on the previous slide, the tightest complexity that is known appeared in a previous POPL paper last year on strong loop, that considered strong loop synthesis. Strong just being the same as our tightest or best aspect here. Loop synthesis might not be so well known, but you can consider it as the kind of sister or opposite side of the problem of invariant generation. Invariant generation being I give you the program and then I want to automatically find properties associated with it. Nico did mention this previously. Loop synthesis goes the other way. It gives the property or the specification and says generate the loop. And you could change this into a decision problem by saying, well, if there is no such loop, you must still output the answer no. Of course, if you constructed a loop, then you should be saying yes. And I should say that there's lots of work, even in just the linear setting. So when I just take linear updates, that might be one linear update in some of these cases. So that will be like where we see the word simple, we mean just a non-branching single path loop. But there could be many, many different updates. I've already shown you one where I had 2 different matrix updates. And that's kind of the point of our paper today. The paper considers 2 problems. I should say, on the previous slide, I said that this was strong loop synthesis. But you could think about the fact that I only had one single matrix, that I'm actually generating a cyclic matrix group and then applying it to some vector. So I can think of this as the action of a cyclic group acting on a single vector. And we'll call that the cyclic orbit closure determination problem here. And it literally says, okay, I've taken my favorite set defined by polynomials, and I ask whether you can kind of explore this set in such a way that I output a loop. You could also ask the kind of appropriate loop question in this, the analogous group question here. So this is a bit more difficult, perhaps. So now, before I gave you a nice set Z that lived in the plane, now I'm giving you a set of matrices. But this is actually just meant to be confusing to you. Think about what a matrix is. So this GLDQ notation might not be familiar to you. Let me explain it. Here I'm taking D by D matrices, so D-dimensional square matrices. Their entries live in the algebraic numbers, so they're pretty nice to go. And this GL just means they form a group in the sense that they are invertible. So if I have a matrix, I can calculate its determinant. So long as that determinant is 1 or minus 1, then the inverse of that matrix also lives inside the kind of group, and you'll get these nice algebraic numbers. So this is what I'm talking about when I look at invertible matrices. But of course, these D by D matrices have D squared entries. So Z is, when I say Z is a subset of matrices, just think of this as points lying in D squared dimensions. Before you saw it in dimension 2, but now we're working in D squared dimensions. And now I'm just asking, well, if I take a matrix or a set of matrices, this Z, is there a group structure inside them? And in particular for this version, is there a cyclic group structure? So now, we've done away with this kind of alpha part that appeared in the previous loop synthesis. Just the results that we have in this paper, this theorem, says that in the cyclic group determination case, actually you can not only give a decision problem, but you can also output the matrix in the case when your answer to the decision problem is yes. Now, the thing that we're going to go from here is, well, I've put this kind of word in brackets everywhere on this slide, cyclic. So can we do any better? And luckily for being a POPL paper, the answer is kind of yes. Yeah, I know, we're not confident about these things. So previously we were synthesizing, i.e. making different linear loops from before, but previous slides just used a single matrix to go through. Now let's do it for multiple matrices, M1 up to MS. And we ask, when we apply these matrices in a non-deterministic or branching path system, can we do any better in this sense? So that means, can we do this nice over-approximation and give the best possible answer in terms of polynomials? And obviously, when I talked previously about the cyclic group determination problem, hopefully you are all aware of groups that are not cyclic, so there's good motivation for just the general case of this problem too. So again, this notation might look scary to some of you, but this set Z just lives in some large dimensional space, D squared space when I have D things working on it. And we're just asking, rather than a matrix, so I should have said my previous notation here where I had these angle brackets and M just meant I was applying M to itself, or maybe it's inverse. So that's why I'm getting this kind of over the top, meaning a closure. Angle brackets is just M, M squared, M cubed, M to the 4, or the inverses. Here I've just got some group G, and really I don't really need the angle brackets here. I can just take the group closure. But the kind of nice thing here is something that didn't appear in the previous slide. Why do we call these determination problems and not just decision problems? And the reason that we call them determination problems is the user also has to give the S, so whether there are going to be S matrices acting on this. So what you're going to do is your inputs, you're going to be given your favorite algebraic set Z. It's always in pink for me. And you're going to give your favorite natural number, and you're going to ask whether you can explore that algebraic set in a way using a group that's generated by S elements. Okay, so the results of our paper say the yes kind of is that we have complexity results in the sense that we have to give a complexity result, I obviously have to give you the full definition of these problems, but that's just parameterizing the problems by saying, well, your algebraic set was defined by M polynomials, and they had certain degrees, and I talk about a zero locus, that's just the set of common vanishing points of that set of polynomials. And I also have to give you the S that I want you to input, and we're living in D dimensions, or D squared dimensions. So the gray boxes are just the hard way of presenting the problems that were on the previous slide, but they allow you to parameterize the problems and then give the complexity output. In particular, all we're saying is that at some point you can get a theorem out of these things. Let's just do one of these problems, or let's just consider one of them. So in particular, oh, there is one last thing I forgot to say. These are the problem statements. The results say we can do it kind of in the sense that we need commutative matrices. We only work in the commutative world. We're not even almost commutative in a kind of nice sense. Okay. I will try and explain where the commutativity comes from, and perhaps I don't have a kind of further work slide, but the whole point is we'd eventually like to get rid of this commutativity problem. The orbit problem, as I said at the start, is undecidable for commutative matrices, but you should always be able to compute orbit closures, but we don't have nice complexity bounds for the non-commutative case. Okay, so what is really happening here? So yes, my one last thing then is that there's an alternative way of thinking about what this non-deterministic loop looks like. And because you have commutativity, you can write the kind of, in the loop setting, these bottom two lines are literally just saying, well, what are the matrices that I can apply to alpha? And because you're allowing commutativity, you can just lump all of the M1s together, lump all of the M2s together up to the MIKs as much as you like. Okay. Without trying to give you the full proof, let's discuss where these kind of bounds come from. So it turns out that, like many matrix problems, you might want to consider a change of basis that works in your favor. For us, we know there is a change of basis such that you can always choose your alpha to have 0, 1 entries. Because there are 0, 1 entries, you're in some kind of finite space, and you're just going to guess alpha in non-deterministic polynomial time. once you have made the commutativity choice, these kind of matrix groups that live inside this specific general linear set, they can be decomposed using something called the Jordan-Chevali theorem. And I'm sure I've just mucked up that name in front of a French audience, and I'm very sorry for this. These are essentially what are called unipotent and semi-simple matrices. I won't go into it, but semi-simple matrices, the GS, they are just going to be the diagonalizable matrices. So these sets are kind of well known in the kind of mathematics community, even if they're not necessarily in the computer science community. And the point is you can tease out this nice group structure inside them, and because you put a generator requirement on the underlying group structure, you actually know that these are also going to be finitely generated. The semi-simple matrices in step 3, they have a lattice structure. This just means they act nicely in some arithmetic way. They'll live inside this nice commutative setting of ZK. And again, because we know something about the generators, we can guess the generators associated with these semi-simple matrices in non-deterministic polynomial time. So finally, if all those things go well, you're at your final step and you're saying, well, I've got this Z and I need to know something about gu.gs.alpha. In fact, the GU parts can be kind of tested. If such a subgroup exists, you can check it in the theory of the real closed fields. But our complexity bounds don't come from checking every type of sentence. The sentences have a specific structure going down inside the kind of matrix group. And they have this kind of what's an existential, universal, and existential blocks. But these stars are meant to be blocks of existential operators, a block of a universal operator, and then a block of an existential. So, final slide. We consider two problems, group determination and orbit closure. Orbit closure being the one that kind of generalizes loop synthesis that we saw at the very start. And when you parameterize the problems in this very specific way, which I've done in this slide, we have polynomial space procedures for both of these problems under the assumption that the matrices commute. Thank you very much.
Okay, thanks. Are there any questions?
Hi, great talk. You had a time complexity bound earlier. Would you? Yeah, so I noticed that this bound doesn't seem to depend on the number of generators.
Yes, good point. I should have pointed this out.
Yeah, I'm kind of curious if you could give an intuition as to why that might
Yes,
be.
thank you for pointing this out. So essentially S, you can always choose to be the minimal one such that it works. Otherwise, you can just add, say, an identity branch to everything and you're not changing anything. And within the kind of mathematical structure, you know that S must be bounded from above by D, which is the dimension that you're working in. Once you've kind of got that under your thing, you actually only need the D. So it's always good to give the S, but it doesn't matter in the final result.
Okay, cool. Thank you.
No, thank you for the good question.
So you investigated these results with respect to real algebraic numbers, but real closed field is a fairly difficult theory. There are lots of problems when you deal with real numbers. Is the problem simpler if you took complex numbers?
Oh, this is a good question. So actually, I should say that I even had a backup presented for this. So I said real closed fields, but in fact, the theory that we're doing for the complexity bound also works over complex algebraic numbers too. So luckily, we can actually rely on the same results in this setting.
Maybe it could be even simpler, no?
Oh, that's a good question. Probably it is going to be simpler, but I don't think we considered it in our kind of dealings. But thank you.
So kind of two
things I was wondering. One, so you mentioned just for commutative groups. One example I would think of like the most mild thing that could be considered that's not commutative, but also would be very interesting would be like the Heisenberg group. Is that
Everyone loves the Heisenberg group.
Because there's also some problems that this would. So like I feel like if you could do the orbit closed, what do you call it, the generation or the orbit problem for the Heisenberg group, plus if you could do it for complex numbers where the kind of invariant you're looking at, it involves the complex variables, but also their complex conjugates. If you could do that, then I think you would solve some hard problems. And so I'm wondering, what is the complication that stops you from doing that?
So in some sense, the Heisenberg groups will have what are called unipotent matrix elements because they are this upper triangular matrices that have ones on the diagonal, which gives us this unipotent/nilpotent structure. And the unipotent matrices are the ones that cause us problems. If you just consider semi-simple, i.e. diagonal matrices, they're the kind of easy ones to tease out because in some if I tell you in advance all of your matrices are semi-simple, i.e. diagonalizable, you can actually choose a change of basis matrix that diagonalizes all of them at once simultaneously. You don't have that kind of fun situation in the unipotent case, which kind of covers your Heisenberg setting. I think also even the orbit problems, so not even these orbit closure problems, are supremely difficult in the Heisenberg case. I would have to check. I know people are interested in the Heisenberg case when you use, say, integers or rational entries for your matrices. We're specifically avoiding rational numbers or integer numbers here because as a backup slide, like the loop synthesis problem, which I considered at the start, is undecidable due to relations to Matiasevich's work. Essentially, you're solving polynomial equations in several variables, and over Q or Z, you either have undecidability or decidability is open. So you've struck a very good setting and definitely a group for us to consider in the future. Whether or not our techniques are strong enough yet, I do not know.
Okay, thank you.
Any more questions? So if I may have one last one. Actually, I was curious, when I think of orbit problems, I usually think of the other way around. I have the group given, and then I'm trying to find out whether an element is in the orbit, right? But you have the
opposite.
You're finding out the group. How hard would it be to find the kind of the set of algebraic equations that cover, like, that give you
so in our paper, we actually divide these two into things. So you're doing what we call an explicit orbit closure problem, and we're doing what we call an implicit orbit closure problem. I.e., in my setting, I tell you the generators, and then I want some so I have some generators, I want to find out some property, and I spit out some polynomials that will then give you the final answer. And I guess the point is that when you work over Q or Z, certain subgroups of the invertible groups in, say, D dimensions have very nice properties. Orbit containment, orbit equivalence are definitely things that have been studied by other people. Whether or not you could kind of translate our results where we're working over algebraic numbers, I'm not so sure, to the kind of explicit versions of the problem that you're asking for. Sorry.
Thanks. Yeah, thanks. This concludes this session. So I think we have a break again now, the poster session. So thank you.